Great. I think we can go ahead and get started. I have too much stuff in my hands already. Just a few housekeeping rules or ideas. If you're in the room and you look up and you see those green lights, that means you're on candid camera and we're recording. So if you're talking to your neighbor, shuffling papers, exclaiming at whatever news thing you're reading on your phone, the mics will pick it up, so they're quite sensitive. If you're speaking, you'll get to use the little microphone that I have here. Don't have your phone in your pocket where you put this, because it'll also pick up static on your phone. So you can put it in your pocket. The microphone should be, kind of sternum high, close to your chest, facing up. If you do this a lot, it also sounds terrible on the mic. Is that it for audio stuff? So I'll give this to Laura. She's our first speaker, and we'll demonstrate how to
demonstrate. Yeah,
how to get mic'd up.
I'm either demonstrating how to do it or how not to do it.
Yep. Because the room mics are on, I won't have to run around with this microphone, but it does help if you kind of, speak loudly so that the people online can hear you. And folks online, I would appreciate lots of engagement here. We've got 120 people signed up for the meeting, which is awesome. And I think 60-ish or so that are signed up in person. So having kind of a robust conversation, some of that can happen through the chat, but it really does help if you're brave enough online to raise your hand and ask your questions. I think that's a great way to kind of maintain the engagement. So I'd encourage you to do that. And then the CGD Code of Conduct is up behind me. The flowers have gone away, but the message hasn't. So there's, I think, a nice way that we can kind of start the meeting by thinking about how we want to act as a community and collaborate and kind of celebrate the wins that folks are going to be sharing today. We have, I think, 4 or 5 talks before the break. The breaks are kind of long by design, and that's to let us kind of engage and mingle and chat informally out in the hallway. If you're online, sorry. But for folks that are here, I'd encourage you to kind of use that time to get to interact with everyone that's here. I think that's it as far as things to announce. So Laura Landrum asked to come and give a presentation about storytelling. And we do have some pretty incredible stories that folks are going to be sharing here. And so I thought this would be a way to kick off the meeting and hear about some projects that are happening at NCAR and across the community.
Thank you, Will. Am I working all right? I think I demonstrated how to do this. Anyways, thank you and welcome. I am just here primarily to increase awareness of an upcoming cross-working group session that we hope to host at the CESM workshop in Boulder this coming June. Storytelling and using storytelling as a tool to craft climate science tools for communities. And this workshop is it's not narrowly defined on purpose. We want to have participants from the full range of those that have experience doing collaborative storytelling with communities to do the work. And those of you that might be interested in learning more about it, whether it's tools or ideas or things like that. And also using storytelling with communities as a way not only to understand better what communities might want or might find useful from the climate science that we do, but also as climate scientists to understand more about what communities are looking at and concerned about, that we can redo things a little bit in our own climate science. And I'll give one really short example. Is I've worked with some communities in the Arctic on trying to understand what they're concerned about. And one of the many things that Arctic communities are very concerned about is landfast ice. And I just thought of landfast ice as this well, that's kind of an interesting project, but not something on a global scale, and we don't put a whole lot of energy into it. But in listening to these people tell their stories, I realized, oh my goodness, landfast ice for some of these communities is a refrigerator. It's a storage system. It's a way of, because they need to have it for 2 weeks in the summer to harvest the seals and properly cure the meat. And it has to be a certain distance from the village to try not to attract polar bears to the village. It also has to be cold and dry. And if that landfast ice is not there and they still are able to harvest seals, they have to reassess how they're going to process them. So that has me looking at my climate science in a different way of, we still don't want our model landfast ice directly per se, but are there other things that I can think about in terms of modeling sea ice and the information that we get that might do risk assessment for landfast ice. So that's just one of many examples. Also, if you have people in your community or yourself that you think would be great speakers or to give a talk about their experience with storytelling and using storytelling as a format for understanding and bringing climate science to communities, please let one of us know. We'd be more than happy to reach out to them and invite them to participate. It's the Extremes, NCAR Extremes group. So that's James Dunn, myself, Melissa Moulton, and Diamond Tachera, and Mari Tai. So feel free to reach out to any of us. Keep us in mind when you see that come up. The schedule has obviously not been set yet for the CESM workshop, but we hope to be up there. We hope to see all of you and have a lively session. Thank you. Oh, you can answer the question.
Is there more than just what's happening at the workshop? Are you guys have other activities or?
So we don't have any other activities planned per se. We want to use this workshop as kind of not only ideas to see how it goes and to perhaps have some activities from this. We've thought about hosting a workshop here at NCAR, and that's just kind of in the specifically for this. We also worked on bringing some of this idea to light. We published an article in EOS last year about it, but no other official activities right now. Yeah. Any other questions? Okay. I actually finished early. You didn't have to give me your red light.
Maybe while I was getting mic'd up, a few other announcements. So Lydia is helping kind of moderate the chat and watch time and all that stuff. Okay, so there'll be a couple of us that are for all the sessions that are moderating and announcing, and then whoever I've pegged to do the next session you're always in pairs, so you and your partner can figure out how to do this. So Lydia.
Andrea is next.
Oh, nice. With
Lydia.
So you guys get to figure out how to do this next. Otherwise, I don't know if it made it onto the agendas, but tomorrow we're going to have a dinner at Avanti, which is on 14th and Canyon. It's at 6:30, but you can kind of show up whenever. And then today, after the session ends around 5, I'm going to head down to the Southern Sun for a pint. And anyone's kind of welcome. Tonight's super informal. We don't have a reservation. I'm hoping that it's not so windy that we get blown off the patio. I guess we'll have to see. But tomorrow at Avanti, we do have a reservation, and there will be kind of tables out through it there last year for those who are here. Those are 2 other social activities that are happening. House stories over some food or a beer.
Do I need?
I was going to ask, should I be switching this, or do you switch this? I get to do it. Oh, you can do it.
I don't know if you have to. Sure.
All right. Our next speaker is Abby Swan, who's going to talk about land carbon cycle responses to net zero emissions.
All right, great. Thanks, Will. As Will said, I'm going to talk about land carbon in these scenarios where we have increasing emissions, then zero emissions, as well as negative emissions. And we're looking across different Earth system models. I just wanted to acknowledge collaborators, Charlie Coven, Christy Protesescu, Rosie Fisher, Ben Sanderson, and a whole bunch of folks who contributed different simulations from other Earth system models, as well as input on our work. And we got funding from NSF and DOE. So as everyone here knows, carbon dioxide in the atmosphere is rising, and warming on Earth has occurred as a result of the radiative forcing of this carbon dioxide. And actually that warming scales with cumulative emissions of CO2. So this plot shows the cumulative emissions along the x-axis and the global surface temperature increase on the y-axis. The historical period is shown in gray, and we can see that, it's not perfectly linear, but it's pretty linear that warming has increased along with cumulative emissions. And it's also true if we look at multiple different scenarios going into this future that this linearity seems to hold, regardless of which of these scenarios we're looking at, which have pretty different time patterns of when those emissions are occurring. And there's a spread in this that comes from physical climate factors like how fast is the ocean taking up heat, what are cloud responses, and anything else that impacts sort of traditional ideas of climate sensitivity. But there's also a carbon cycle component to this. So the carbon sinks in land and ocean are also impacting this because it's basically a balance between the rate at which the system is taking up heat and the rate at which carbon sinks are drawing down CO2 out of the atmosphere. So this is an emergent relationship. The fact that those two factors seem to be going at about the warming associated with the carbon drawdown is going at about the same rate as the heat uptake by the system. And so the uncertainties in these physical factors, but also in the carbon sinks, is important for determining this response. And it's something that I think is underexplored. And so we're going to look into it a bit today, as well as what happens when we stop moving along this x-axis when we bring annual emissions to zero. And a lot of that uncertainty in the carbon sinks is coming from the land. So if we look across these different Earth system models in these different colors, we can see the land sink on the left and the ocean sink on the right. And we have a huge spread in what the land sink is doing as emissions are increasing. And we still have a spread in the ocean sinks, but that ocean sink response to this extra carbon in the system is just the spread is a lot smaller than the spread across different land models. And I sort of, in a very simplistic way, talk this up to the fact that the land carbon uptake depends on all these biological processes, which are highly uncertain, interacting with climate that are coming out different across different Earth system models. And the ocean sinks are just more dominated by physics and chemistry and upper ocean on these timescales. So the uncertainty in the land is really large, and we would like to understand it better. So we're going to look at these experiments called Flat 10, which are part of the fast track for CMIP 7, where there's emissions of 10 petagrams carbon per year that then go to zero in year 100. And this is about the rate of current fossil fuel emissions. And just as a reminder, all of these simulations are emissions-driven simulations, meaning that the atmospheric carbon dioxide is prognostically calculated as a result of the emergent land and ocean carbon sinks. So the cumulative emissions associated with this, like we were looking at on that x-axis, look like this. They increase till year 100 and then they stay flat because we're no longer emitting carbon, but we've still cumulatively emitted carbon. So that's kind of our first expectation for what temperature should do as well. So we're going to look at 2 time points here. We're going to look at what happens after we've had this period of positive emissions, and then we're going to look at after we've had a period of zero emissions for a long time. I'm going to look across these 10 Earth system models. Don't worry about keeping track of which one is which, but CESM, I will show you more examples from, is in that sort of yellow-green color. As a background point to make, the pre-industrial carbon stocks in these models vary a lot. We're looking at zonal plots here from the North Pole at the top to the equator in the middle, going down here to the southern hemisphere on the bottom, and soil on the left and vegetation on the right. And I've just plotted an observational present day estimate in the shading in the background. And each of these lines is the Earth system model's pre-industrial carbon stocks. And just to point out that they sort of have wildly different pre-industrial carbon stocks. And that's something that we need to take into account. In particular, really widespread in tropical vegetation carbon and high latitude and mid-latitude soil carbon. So let's look at their response to change, keeping in mind that there is a pretty different background state. Well, in this period of positive emissions, we have atmospheric CO2 increasing. We have global mean surface temperatures increasing along with that. And so we have higher temperatures, more carbon dioxide. What's happening to the land sinks in these models? And we find that land sinks also linearly increase. There's maybe one maybe that cyan model is looking like a little bit less than linear increase, but pretty much all of the rest of them, they have different slopes, but they're sticking with their linear increase of land carbon along with emissions. So they're taking up carbon during the emissions phase, but there's a little bit more to it than that. If we, if we continue those emissions, so now I told you we were going to zero, but just imagine we continue emitting at that same rate into the future. We do see that some of them start to taper off. So they don't continue taking up carbon linearly forever, but some of them do. And so there's a bit of diversity here in what's happening as we extend beyond cumulative emissions of about 1,000 petagrams. And to me, this seems very optimistic that the system could continue to take up this much carbon, and thinking about, are we adequately representing the heat stress and the water stress? I mean, these models must be getting very, very hot as we're getting to cumulative emissions of 3,000 petagrams of carbon. And yet the pink and purple ones are just continuing to increase. And we could ask, well, maybe nutrient dynamics are related to this. Maybe the dynamic nutrient models might be showing more of this tapering off. But actually, if these models all have dynamic nutrients in them and they span the full range of the response. So I don't feel like this is not a full analysis of what could be going on here, right? We have different initial states. We might have different interactions with what the ocean is doing and atmospheric CO2. But at first blush, it's not necessarily that they have different nutrient dynamics occurring. Okay, so they happily take up carbon on land, but actually there's a little bit more to it than that. Mostly they're taking up this carbon in vegetation. That also makes sense, right? The first thing that would happen with high CO2 is that we get vegetation growth, and that might get transferred to soils. So this is the CESM example here on the right, where we have vegetation in the shaded wedge and soil in the solid wedge and a teeny bit of litter in the white. If we look at this now zonally, so again, we got the equator in the middle there and the North Pole at the top. During this emissions phase, we broadly see big increases in vegetation carbon, but they're concentrated largely in the tropics, as well as some gain in mid and high latitudes. And this is kind of broadly true across models, which I'll show you in a moment. So here we made CESM small, and I'm going to show you all of the models together here. And you can see that broadly they are increasing vegetation carbon a lot. That's the light shaded area with the diagonal lines. And there's more modest increases in soil in most of the models, but some of them still see some significant soil uptake. So we kind of have this bulge in mid to high latitudes and a bulge in the tropics. What happens if we extend into this period of zero emissions? Well, temperatures flatten off as we expect sort of first order from the cumulative emissions. They increase till year 100 and then they're flat. But the carbon dioxide in the atmosphere is starting to drop. And that's because even though the temperature is staying constant, the land and ocean sinks are still drawing carbon out of the atmosphere. So we're not emitting carbon into the atmosphere anymore. And so the carbon dioxide is going to start to decrease as those sinks are operating. So this is an interesting time to think about plant responses because the temperatures are still really high, but the CO2 is starting to drop, and any benefits from that CO2 will be starting to go away. So let's look at the end of this time period and see what has changed from the point of net zero. So we can see for the total carbon on land that it follows a relatively similar pattern to temperature. It increases and then stays relatively flat, but you can see a few of these models are showing decreases in total land carbon over this time period. We can break that down again into vegetation and soil globally. This is for CESM. And you can see CESM overall is pretty flat, but the contributions from soil are increasing over time and the contributions from vegetation are decreasing. Its wedge is getting a little bit smaller. CESM is more modest in this than some of the other system models. So vegetation is still taking up most of that extra carbon, but it's declining over time. And if we look at the zonal distributions, again, we have the same plot on the left of what the extra carbon that got taken up during positive emissions, and we compare that to this, what happens after we've been at zero emissions for a long time. We can see that the tropical uptake of carbon is really minimal in CESM, starting to diminish. Some in other models, it's starting to be lost as well. But we're still gaining carbon at mid and high latitudes. So the soil carbon is increasing and vegetation carbon is increasing, except for those very highest latitudes where maybe we're starting to see some loss from permafrost. So again, we can compare this to other models and see that this is sort of broadly true across the Earth system models, where we're getting losses of tropical carbon there around the equator, and it's largely losses in vegetation, although some models lose soil carbon as well. So it's pretty modest changes in the tropics, but most of them are still gaining carbon in mid and high latitudes. And so that's interesting to think about if that's just transfers from those vegetation pools going in, or if those mid-latitude systems are responding well to these warmer temperatures, despite the fact that CO2 is diminishing, and if we think that's reasonable. So Earth system models sort of are taking up carbon while CO2 is rising, but the tropical sinks are starting to turn into sources under hot conditions with declining CO2. The mid and high latitudes are continuing to gain carbon largely in soil. Now I want to think about what happens in a negative emission scenario. So these are magical negative emissions. We haven't said how they've happened. We've just removed CO2 from the atmosphere in this blue line. So we have the same emissions phase, and then we start declining the emissions, and we pass right through zero all the way to -10. So the simulations reach net zero at 150 years, and then we stay at -10 emissions all the way to 300 years, at which point we've taken out the same amount of CO2 that was put in during the emissions phase. So we have cumulative zero emissions. And this allows us to look at some of the reversibility of the system. So we put all this carbon in, and then we take it back out again. What happens to where the carbon goes on land? And so the cumulative emissions look like this. We come all the way back down to zero. So let's look at this this period of negative emissions to zero cumulative emissions. We see that temperature does basically what cumulative emissions does. It peaks and then comes back down. Similarly, atmospheric CO2 peaks and then actually declines below what pre-industrial atmospheric CO2 is. If we look at where the carbon is going on land in CESM, we can see that the vegetation carbon is starting to turn over at an earlier time than the soil carbon. So vegetation carbon is responding to this change more quickly, which is sort of what we saw in the zero emissions as well. The soil carbon is delayed, so it has a peak that's occurring a little bit later. If we look across the models at the total land carbon, we can see that they have some variation in when that total land carbon peaks and then starts to decline. But it's not a huge amount of variance. However, they're actually very consistent in their vegetation timescales, and they're wildly inconsistent in their soil timescales. So their timing of, I didn't show it here, but the timing of peak vegetation is really similar, and their timing of peak soil carbon is, I would say, all over the place, meaning that there's really a lot of difference in how they're representing how the soil pools are responding to these changes and these negative emissions. So the reversibility of the soil and the timescales associated with that vary a lot, which maybe doesn't surprise anyone who thinks about soil carbon, but worth pointing out that there's large differences here, which will affect the longest timescales that we have for land carbon cycling and the reversibility. And so we can look at this zonally as well, and we see sort of broadly similar actually to net zero emissions, that they're still gaining carbon in mid and high latitudes, but the tropical carbon is becoming a source. It's just a loss of vegetation carbon in CESM, which is relatively modest, but if we compare it to the other models, we can see pretty big losses in vegetation carbon in the tropics, while we're still gaining carbon, at least in the mid latitudes, and a little bit of loss in the models that have permafrost like CESM and NOR-ESM. Okay, so some take-home points. The tropical carbon has big gains with emissions, but also big losses under zero and negative emissions. This suggests that those tropical ecosystems could be quite vulnerable to carbon loss as we go into this period of hot conditions where CO2 will be dropping. The mid and the high latitudes are tending to gain carbon after zero and negative emissions, but we should these ESM land carbon sinks are, I think, probably optimistic based on the way that they respond to those increasing emissions without slowing down. So thinking, I know we've been talking about this forever, but we know what are the missing things that might make these carbon stocks vulnerable: mortality, pests, pathogens, water stress, heat stress, et cetera. And if this were true, then those tropical carbon stocks might be even more vulnerable, and maybe we would see more modest increases in those mid and high latitude carbon stocks. And we see a big range in timing of soil carbon changes across models. And this is the longer timescales, which could be important for the role of the carbon system in general in setting the climate sensitivity response to these changes in emissions. Okay. Oh, and then this picture in the background is actually the zonal and then temporal change of the land carbon over time. So you can see it gaining that big pulse of mid and high latitude carbon in the middle, and then turning pink, becoming carbon sources later in the simulation. Thanks.
We have tons of questions, unfortunately. But maybe as Abby's, if everyone has a quick question while Abby's trading the mic over. Put Audrey on it. I have a question. Oh, go ahead.
Thanks, Abby. I want to ask about the pink, right? So, but it looked like across the different models, like CSM and NORSM showed the opposite response in tropical carbon in the flat experiment, like where it was remaining a zinc, right? Is that right?
CSM becomes a slight source in the tropics.
Okay.
That was actually seen on our own that we were looking at there, so it wasn't the same model. But most of them become a source in the tropics. Maybe one doesn't. Yeah.
Sorry.
Okay. Sorry, we have to move on. I'll talk to you later.
Catch you at the break.
Sorry.
Awesome stuff. Okay, next up, Adriana is going to talk about some work that she's doing with the CESM2 large ensemble.
Thanks. And if you came to my CGG seminar, I apologize that this is going to be a repeat performance. But anyway, yeah, so I've been doing this sort of side project using the lens. And actually, there's going to be pretty much no like carbon land variables, just going to be climate variables, but very land focused talk. So yeah, so I am an ecologist. And so as an ecologist, our big questions is how do ecosystems change when climate changes? And, this is a really relevant question today, obviously, but it's also been a question for centuries. And so, as early as the 3rd century, the Greek philosopher Theophrastus was conducting ecological experiments like transplanting plants outside of their natural range to see how they would grow and documenting changes in phenology with climate. Alexander von Humboldt in the early 19th century was really interested in how physical and biological processes shape the globe. So this, one of his early publications is this schematic of Mount Chimborazo in the equatorial Andes. And so you can't really see, but there are plant species and animal species listed at the elevation at which they grow. And so in the 19th century, when he made this was kind of a really big deal to him that, plants and animals are found in different locations in elevation and in latitudinally, depending on climate. And he was really interested in temperature specifically. And then 1947, this guy, Leslie Holdridge, developed the Holdridge life zone system, which relates climate and vegetation zones, which he called life zones, using indices of temperature, precipitation, and aridity. And this system has been used to evaluate regional and global vegetation patterns using quantitative measurements of climatic conditions. And so he saw this as an improvement on the previous methods because it added these 2 new climate variables. And so this sort of biogeography kind of perspective, in terms of climate science, we might call this climate space. So being some kind of multi-dimensional set of climate conditions that describe a location on the globe, particularly as it relates to vegetation and or animals. So if we have some measure of performance, and then and the x-axis is temperature, and so it's warmer versus colder. So that can either be equatorwards or lower elevation or polewards and higher elevation. And then there's some optimum temperature at which this species likes to live. And then if we think about it in 2D space, we can maybe look at rainfall versus temperature, and then there's some sort of envelope where that species lives. And then spatially, we can kind of think about there's some distribution of that species across that range. Okay, and so then if we get a change in climate, that optimum temperature is going to move. Similarly, for our 2D space, we're going to get a contraction of the range where it's no longer suitable, and then maybe an expansion of the range where it's now able to live where it couldn't before. And then if we see spatially, we might get, so we've got, a shift in temperature, that species might move, and then we might actually see it expand into a new range, and then we might see invasion of a new species that can now live. Okay, so this idea of climate space applies to all biota, but for this talk, I'm going to focus on vegetation. And what happens to vegetation is not only important because vegetation, as we just heard, is very influential on climate, but also because of their role in ecosystem services, like providing habitat, lumber, crops, and even things like flood mitigation. And then we like to go hiking, right? So. Okay, so in the face of changing climate, we have seen plant species migrations in the past. So for this, for example, is a map of jack pine distribution superimposed on the current jack pine distribution in gray, and then superimposed on the Laurentide ice sheet. And we can see these red dots are where we have pollen evidence of jack pine, and the red lines are sort of these estimated migration paths. And again, I'm talking about plants. So these aren't trees obviously like walking up and moving. It's has to do with the species itself. So the seeds are traveling and then new species grow up. And then in northern New Mexico in the 1950s, the ecotone between semi-arid ponderosa pine forest and pinyon juniper woodland shifted extensively through mortality of ponderosa pines due to drought. And then currently we're seeing evidence of biome shifts in the boreal zone. So here is an example of a baby white spruce tree that's growing in the tundra in north of the Brooks Range in Alaska. And then we're also seeing boreal browning in southern Canada, which is kind of evidence for some boreal contraction. So for this project, what I wanted to do was to quantify potential shifts in biomes and climate space using Holdridge life zones as a structured framework. So the idea is to treat these Holdridge life zones as a kind of climate space or climate envelope, and then as well as a classification system. And so, as I said, the system relies on 3 different climate variables. So biotemperature, which is just average annual temperature, except it's capped from 0 to 30 degrees, which will be important later. Average annual precipitation, and then average aridity, which is just PET over, precipitation. So for each of these little hexagons, there's going to be, we can calculate what the centroid of that hexagon is to say like, okay, for boreal wet forest, you know, the biotemperature is 4.2, the precip is 700, and the aridity is 0.3. And then similarly for, okay, there we go. Cool temperate forest. It's increased in temperature and precip, but the aridity stays the same because we're on this sort of aridity axis. And then if we have a grid cell there, we want to know, okay, what is my biome? We can classify that. It's not working by looking at the difference between all the centroids and that grid cells, biotemperature, precip, and aridity. Take the difference, and then actually, if you may have noticed this, but this triangle, everything's on the log 2 scale. So, okay, okay, so yeah, we're going to add up the differences, but we're first going to log 2 scale the difference. So that kind of makes it so that the precip isn't dominating everything, because you ever notice it's like 1600 by the end. And then if you square those and take the square root, that's actually the Euclidean distance. So what we're going to do is minimize the Euclidean distance for every grid cell, and then you find the minimum one. That's what your biome is for that grid cell. Right. Okay, and so for this project, I applied this framework to the CESM2 large ensemble, which allows for quantification of uncertainty in climate space, and then biome projections due to internal climate variability. And so for this project, I used 90 ensemble members from the lens. So that's going to result in 90 different Holdridge life zone systems for each simulation year. And because the classifications are quantitative and you could get sort of like wiggling year to year, and generally if you were going to do this for like an observational data set, you would want to base it on long-term climate conditions. So I wanted to minimize that wiggling. So I took a 10-year rolling average across this output. So that's going to actually be 1855 to 2095. And then I did this for the original lens, which is SSP3. And then I also added in SSP2 and 5, which are smaller sets of ensemble members, but it's good to compare. Okay, so here's the classification for year 2000 on the top. And this is just using an ensemble average just so we can look at a map. But and then 2100. And you can maybe kind of squint and see that there's a difference between those 2 maps, but it's really hard because there are 38 zones. And actually this is like half of the zones because I'm only looking at the latitudinal zones, not including altitudinal zones. So you can actually have polar tundra and alpine tundra, but I'm just looking at the polar and tundra considered the same here. So what I ended up doing was, as in a couple other studies that use this method, I aggregated those 38 zones into 13 collapse zones, which just gives better analysis and interpretation. So that's 13. Okay, so because I used the whole lens, we can actually look at the probability of shifting life zone between year 2000 and 2100. So that's just, across the lens, what's your probability of shifting? So we see areas of high probability of change in the boreal and Arctic zones. And then interesting, like no change in the tropics for some reason. That seems kind of odd. And actually, a lot of studies that have looked at biome shifts have said that the tropics are the most stable zone. But if you'll remember, this triangle is built using biotemperature, which is annual temperature cap from 0 to 30 degrees. So, right. So if you are a grid cell, if your annual temperature is above 30 degrees, you're going to just stay at the tropical biome. You're not going to actually change at all. So here's looking at your 2000 biotemperature zones and your 2100 biotemperature zones, and then the difference. And we see there's large areas in the tropics that don't change at all. But so the tropical is, 24 to 30 degrees biotemperature. So if you're above 30 degrees, like what are we? We don't know. Maybe that's okay. In 1967, this is when Holdridge developed his system. He actually developed it for, that star is way off, but it's supposed to be in Costa Rica. I don't know what happened, the map moved. Okay, but anyway, this is the across the lens, the probability of, or like I think it's anywhere where the annual temperature is above 30 degrees. In 1967, it's like two very small places. So in 1967, Holdridge actually thought like plants can't live at 30 degrees, above 30 degrees C. So there's no point in including it. This is actually looking at the proportion of land exceeding 30 degrees C annual temperature. And so up until like right before 2000, it is pretty much 0. And then it shoots up for all 3 SSP. So, and this is the proportion of the land or the probability of exceeding 30 degrees C by 2100. So it's a lot of the land actually. So we really isn't fit for purpose in the Anthropocene. So what I ended up doing was adding 3 new collapsed life zones for super tropical desert, dry forest, and forest. And so, yeah, here is a map of that using the collapse zone. So 2000 to 2100, and you can definitely see changes. So here in the boreal and Arctic, we're seeing the boreal moving north as well as cool temperate moving north. We're seeing in southern Canada, subtropical desert and steppe moving northwards. In Europe and the Northeast, we're seeing warm temperate forest replacing cool temperate forest. And then in the tropics, we're seeing this sort of new arising of the supertropical zones that I created. So we are actually seeing differences in the tropics. Okay, and then here, that was for SSP3. And so here's SSP2 on the top and 5. And really, it's just a less extreme and a more extreme version. But I'm just going to skip back to that for time. And so then in southern Canada, we're seeing, so this is just looking at net land area change. And so we can see big changes, especially in these new supertropical zones. And then I'm actually just going to shift through all of this for time. But so if we want to look at where the biomes are going, this is a really crazy graph, but essentially the tundra is mostly going into boreal forest, some into cool temperate. The boreal forest is mostly going into cool temperate. And then, and then in the tropical, we have a lot of stuff going on. And then here's all of it. But there really isn't that much change in the percent of biomes that are shifting between SSP2 and SSP5. It's like a 10% change. So maybe that's a little scary, but so if this is our probability of shifting by 2000 or 2100, we're seeing like really big areas of change. But if we want to look at a single grid cell, this is in the Brooks range. So we are here. We can see that we're sort of already shifted, which is kind of true. Like this is where we saw that white spruce tree. So the trees may be behind, but the climate is already saying this is a boreal grid cell. We can look at Toolik Lake, which is tundra, but by 2100, we think it's going to be boreal. Here's central Canada. It's boreal, but we think it's going to shift to steppe, which is like deserty. And because you can see like these differences, though the final life zone is like we kind of agree across the lens, it's really the timing that is sort of the more uncertain. And so this is just looking at the probability of experiencing persistent life zone change for this grid cell from to 2000 to 2090. And so by 2090, we're at 100%. But like, it's sort of like in this zone where we're unsure when it's actually going to happen. So I think that's kind of the interesting part. And so you can look at these big maps of probability of experiencing this persistent life zone change. And sorry, and you can come talk to me later, but okay, the conclusions. Okay, so climate space is predicted to shift rapidly. It's happening now, and then many ecosystems are projected to shift. So, but the timing may be uncertain. Thank you.
Appreciate how challenging it is to tell a whole story in 15 minutes. Awesome. Quick question for Adriana while we're switching the mics over for Kyle. Yeah, go ahead, Peter.
Fabulous talk, Adriana. I'm wondering how you take into account higher CO2 levels for water use efficiency and carbon fertilization in those biomes.
Not at all, right? Because it's just based on those climate variables.
Right.
But that's what, so at the end, if you didn't, I was going to say that the climate is shifting and so it's becoming more suitable, but that does not necessarily mean that the plants are going to shift, right? So we need dynamic vegetation. Thanks. So that was going to be hard to admit that slide, but yes.
And we'll get to hear more from Adriana about PACE tomorrow. So, all right, Kyle Nardi is up next. He's a postdoc, an ASP postdoc working on an atmospheric river event that hit Glacier National Park.
Thanks, Will. Does it sound okay? Excellent. Thank you. So as Will mentioned, my name's Kyle. I'm a postdoc here at NCAR in CGD and EDC. And I'm going to tell a story that's in progress about how we are trying to use CESM to understand how extreme weather events will impact national parks. In this case, we're going to be focusing on Glacier National Park. So I wanted to give a quick shout out to all of my collaborators. This is one of the reasons why I wanted to come to NCAR to do my postdocs, because such a great team and support network that's available to me here throughout different labs at NCAR and also with external partners as well. So I thank all of them. So to orient you about the event we're going to be exploring. So in November 2006, there was a significant rain on snow flooding event that occurred at Glacier National Park in the state of Montana. So between November 6th and 8th, there was a combination of factors: above average temperatures, heavy precipitation falling on top of the existing snowpack that produced a lot of flooding and runoff and produced a lot of damage for park infrastructure in Glacier National Park. Rangers took several of these photos during and after the event, and this underscores the damage that occurred during this event. In particular, going to the Sun Road, which is the major throughway from the west end of the park to the east end of the park. Also, Many Glacier Hotel, which is a major stop for tourists when they're staying in the park. These pieces of infrastructure were significantly damaged, and these are key access points for a park like Glacier National Park. Fortunately, it occurred during the off-season, but more than $5 million was needed to repair these pieces of infrastructure prior to the start of the next tourist season. And I really like showing this quote from one of the rangers, just underscoring the extent of the damage and what these kinds of events can do to park infrastructure. And you might ask, why does this matter? Why are we looking at national parks? And these are photos that I've taken in the last few years that have highlighted my experience with national parks and public recreational lands. And as you're looking at them, you might notice some things that are familiar to you, or maybe recall some experiences you had at parks. And national parks and public recreational lands provide us with so much. Health benefits, physical and mental, for visitors, especially in these times, is really important. Economic benefits for communities surrounding parks, and these are oftentimes rural communities, very politically diverse communities that rely a lot on these places for tourism, but also for cultural pride. Important natural resources to sustain life. We've heard a little bit about the importance of ecosystems, and for humans, for plants, for animals. These areas are really important. And cultural resources, cultural history is really tied up in a lot of these public recreational lands, and national pride and morale. And the whole goal of my project is to find ways to go to communities to bring a model like CESM as a tool that we can then work together to help these communities solve their local problems. And this project specifically is going to be focused on Glacier National Park. It might not be applicable, what we're finding, to other parks, but that's okay. We're mainly just focused on how can we help this particular community with a tool like CESM. So meteorologically speaking, so I come from an atmospheric science background, so I'm going to try to explain what we're seeing here if you're not familiar with some of these phenomena. But what we had was a family of atmospheric rivers. So these are plumes of high water vapor transport in the atmosphere. What I'm showing here in this movie is water vapor transport. Darker colors imply more water vapor being transported in the atmosphere. When these features hit land masses, especially mountainous terrain, you get a lot of uplift and you can get a lot of heavy precipitation. And I want you to notice as the movie starts again, as we get to around November 6th, you're going to see one of these plumes going over the orange triangle, which is Glacier National Park. Atmospheric rivers bring several things: warm temperatures, strong winds, and heavy precipitation. And these are all ingredients that can conspire to produce rain on snow flooding events, as occurred in November of 2006 in Glacier. So my project has two main objectives. First, to determine how well a model like CESM can depict key physical processes that govern this particular rain on snow flooding event. And I want to emphasize again, just this particular rain on snow flooding event. And then if we can establish that CESM is adequate for purpose, can we use CESM as a tool to understand how this exact same storm would affect Glacier National Park in various plausible future scenarios? For this talk, I'll just focus on this first part here, the adequacy for purpose part. So give a few details about the setup we're using. So we're using CESM3. We're using hindcasts or initialized reforecast, where we're using CESM almost as a weather model, where we're initializing with ERA5 atmospheric conditions and NOAA sea surface temperature data. And we're running the model for several days, as we would with weather model, to see if we can reproduce this November 2006 event. But we're using initial conditions from that time period. And we're using a 12-month land spin-up process with ERA5 atmospheric forcing, so that we can get a land state that is consistent with what our initialized atmospheric state is. We're using a variable resolution grid, a spectral element grid in CAM and also in the land model. We're running 1 degree globally, and then we are gradually refining to 1/16 of a degree over Glacier National Park. So where that darkest square is where Glacier National Park is. And then importantly, we're nudging the atmosphere to ERA5 conditions. So above the well-mixed layer or the boundary layer, so in the free troposphere, we are nudging the CAM output to ERA5 so that we are controlling for any large-scale circulation biases, and we can hone in on specific low-level atmospheric and also land processes that could be governing errors in CAM. And so just schematically how this is working. So we'll work backwards from the event. The event occurred on November 6th to the 8th. We initialized at 0Z on November 4th, and we run for several days with ERA5 and NOAA sea surface temperature data. And then moving backwards from that, we ran a 12-month land spin-up with forcing from ERA5. And we're currently working on refining that particular process. Okay, so how does the model do? So we have a couple of biases that we noticed that we want to explore in more detail. So first, I'm showing the change in snow water equivalent from initialization with the baseline configuration we're using, and also SNOWTEL. And we're using a suite of SNOWTEL observations highlighted here in yellow and doing a regional average. And we'll note that snow depth initializes too high at the start of the initialization, and we're currently working on this. You might not see that from the Delta Suite specifically, but we're working on better initializing the land surface. We have a couple of ideas for that. And the thing I really want to note here is that when the rain on snow event occurs, so around November 7th, 6th and 7th, there isn't enough snow melt compared to SNOWTEL observations. And that's something that we're trying to address so that we can get the runoff correct and to get the full scale of the impacts from this event. So snowmelt is too low in the model by default, and that's one thing we want to explore more. We also see that there is a cold bias. So 2-meter temperature coming from CAM, coming from the atmospheric model, is consistently too cold leading up to the event. And we hypothesize that the cold near surface in the atmosphere is preventing sufficient snowmelt during the event. This is something actually I learned from some folks here in CGD, and it's something we explored, and we found that, yes, this actually is something that could be impactful. And so we want to address this a bit. And so we're asking the question, can the tuning of parameters in the atmosphere and the land models improve modeled snowmelt? And as a proof of concept, we're going to increase a turbulent mixing parameter in the parameterization of atmospheric turbulence. I could talk to you offline about what this parameter does specifically, but it essentially governs the amount of vertical mixing in the boundary layer. And we feel that this could then affect scalar fluxes of temperature and moisture, could affect thermodynamic profiles, which then would affect potentially fluxes into and out of the snowpack. So last few slides here, I'll show some preliminary results where we actually changed this parameter and what did we actually see. So what I'm showing here are vertical profiles over the Glacier National Park region from different configurations where we changed this mixing parameter. Blue colors are low mixing, and then the pink color is the highest amount of mixing. And what you might notice in the middle is that momentum flux increases as we expect, because we're increasing the amount of vertical mixing with that pink line. So that's going to have the most turbulent mixing, the most momentum flux. But we also have an impact on air temperature. So we started out with low mixing, we had a temperature inversion. The warmer air aloft wasn't efficiently mixing downward towards the surface. But with the higher mixing scenario, we're able to more effectively mix downward that higher temperature, and our near surface temperatures are increasing then. And we also get an impact on heat flux as well. And we hypothesize then that this could impact our snowpack and fluxes into the snowpack. And this is something that we start to see. So I'm showing here a comparison. So this is the region over Glacier National Park with the native grid. And we have temperature for low mixing on the left, high mixing in the middle, the difference on the right. What you'll notice here is that we're getting an increase in near surface temperatures, in 2-meter temperatures coming from CAM with the high mixing. And we also get an impact then on sensible heat flux. So we're having a higher magnitude of flux going downward into the surface, which we hypothesize is then impacting the snowmelt in the higher mixing scenario. So near surface temperatures are being impacted. That's then impacting fluxes into the surface. I don't show latent heat fluxes as well, but those are also impacted. And so when you look at snow water equivalent between the low mixing and the high mixing, we do get an appreciable change in SWE during the event. So at 12Z on November 7th, we have lower amounts of snow when we have the higher mixing, which we feel is consistent with the higher near surface temperatures. And then that's going to have an impact on surface runoff as well. So in the last minute or two here, I'll just share where we're going with this particular work. So the goal here, I just showed a one at a time parameter sensitivity analysis, but the goal is to change a lot of different parameters. This is a very bad hand-drawn schematic. I'm not a very good artist, so bear with me here. But as an example, let's say we have a plot like snow water equivalent or snow depth. Maybe the thick black line there is the observation. And then the thinner lines are maybe model output from different parameter combinations. And we can do this for a lot of different parameter combinations using, for example, Latin hypercube sample. And we get a range of outcomes. And maybe we find that some parameter combinations get us closer to the result. We can take those, maybe the ones that are highlighted in red, take an average, and then feed that into another level of a perturbed parameter ensemble. But now instead of perturbing the atmosphere parameters, we could perturb the land parameters. And we could do the same exercise and find gradually a subset of the parameter space that is getting us closer to observations in both CAM and also in CLM. And then the ultimate goal is to use this multi-layer PPE to find a suite of plausible configurations that are adequate for purpose, which will then launch us into the second point that I mentioned earlier, where we will use those combinations, those parameter combinations that are getting us adequacy for purpose. And we are launching counterfactual simulations where we say, let's produce that same storm, but in a different climate scenario. What do we get? And then that information we can bring to park managers to gateway town community leaders to make decisions about how to prepare for these events. And then last few slides here. This is just now a first attempt at our CAM PPE. So that first diagram I showed, we're starting out with perturbing 15 parameters. You don't need to focus on what these parameters are, but on the right side, you'll see that there are different parameterization schemes that we're looking at: convection, microphysics, and then also turbulence. And we're exploring a variety of these parameterization schemes. I just wanted to show that we're looking at a lot of different parameters that are impactful for things like clouds, vertical mixing, and also precipitation. And then here's an initial result. So we're starting to get some results where we can start to telescope in perhaps on some of these impactful parameters, and then which of these configurations are providing us with results that are close to what we're looking for. And this is my last slide, so I'm going a little over. Yeah, feel free to reach out if you have any questions. This is still very much a work in progress. And yeah, my PhD was using aquaplanet, so I tried to avoid land for most of my PhD, and now I'm working with it. So I'd love to learn more about ideas that you all have. And yeah, thanks for the time. Present.
Thanks, Kyle. Our next talk is online, so as we're transitioning, Kyle, maybe you can field a question.
Yeah, so next talk, there are a lot of different national parks that are subject to like a lot of different hazards. And I guess you're honing in on one really specific case. Is this something where Glacier National Park or the communities around it have suggested that they need guidance, or do you have a plan for interacting with those communities to sort of understand what is the scope of hazards that they might be capable of responding to with better information?
Absolutely, that's a great question. So I'll be visiting the community in May, the gateway communities of Kalispell and Whitefish, and then also the park itself, to get an understanding of what they're interested in, what metrics they're interested in. And as I mentioned, like, I want this to be specific to each community. So really going in and understanding what the community wants, and then how we can use CESM to answer those questions, acknowledging that those questions might be different and the methodologies might be different. But yeah, so the engagement part is hopefully going to be coming up in a couple of months. Okay. Thanks.
Well, grab Kyle if you've got more questions. That's great. Our next talk is online. And Nora, looks like you're sharing your screen. Can you hear us?
I can hear you. Can you hear me all right?
Yeah, you sound great. Yeah, take it away.
So, hello everyone. I'm Nora. I'm a PhD student at ETH Zurich, and today I would like to present Unpacking the Potential, how proposed reforestation scenarios shape global and regional temperatures. Now, reforestation is quite a promising solution for carbon dioxide removal, and with the recent interest, there have been lots of different reforestation potentials that have been proposed, ranging from 150 to above 1,000 million hectares. But as we all know, trees don't just take up the carbon, the biogeochemical effect, but they also alter the physical properties of the land surface, so the biogeophysical effects. But so far, there hasn't really been a quantification of those biogeophysical and biogeochemical temperature responses to those different reforestation potentials in an Earth system model, which we would need to give recommendations which reforestation potential is actually suitable for climate change mitigation. So to fill this gap, we chose 3 different reforestation potentials by Bastin et al. 2019, Moustakis et al. 2024, and a slightly altered SSP 126 scenario. And we basically performed simulations with SSP 245 concentrations and a fixed 2015 land cover baseline. And then from that baseline, we're branching off to our 3 different reforestation potentials, ramping up reforestation until 2070 to 100%, and then having 30 years of constant land cover. And I should note that we're only reforesting urban land, not reforesting urban land, and very limited crop areas. And so those simulations we performed in a fully coupled CSM2, and we did 5 ensemble members for each simulation, simulating the biogeophysical responses. But the biogeochemical global mean temperature changes, we can then calculate
through the TCRE and the carbon land uptake. And so then from that, our main research questions are related to how global biogeophysical and biogeochemical temperatures are changing and how this is playing out regionally. And so if we look at those three different reforestation potentials, Bastam, Stakis, and Herd, we see that there are some similarities between them. For example, all of them put reforestation in the Amazon, around the Congo, or the eastern United States. But there's also clear differences. Bastam and Stakis have a relatively similar reforestation area of around 900 million hectares, but the spatial extent and spatial pattern is completely different, with Bastam having very large reforestation in high latitudes, and Mustakis having much more reforestation locally and regionally. And the herd potential, on the other hand, is only roughly half the size of the other two potentials. Now, how are our global mean temperatures changing in response to those reforestation potentials? Now, what we see is that for the Mustakis and the herd, biogeophysical global mean temperature changes, they're really not significant throughout the whole time period. But for the Bastam potential here in pink, we see that towards the end of the century, we have a biogeophysical warming that is statistically significant. Now, the biogeochemical temperature changes show a cooling, not very surprisingly. And if we put those two responses together, we get the net global mean temperature change. Now, Mustakis leads to a cooling of around 0.25 degrees, and Bastam and Herd lead to a cooling of around 0.13 degrees. Now, this was actually quite surprising because the herd potential has 450 million hectares less, so the size of the EU, less forest, and nonetheless, it is reaching the same global cooling, just by how the trees are planted in different locations. And so if we look at the patterns more spatially for the biogeophysical response, what we see is that the main reason for this is that in Bastam, we have very strong, mostly albedo-driven warming in higher latitudes, counterbalancing some of the biogeochemical cooling. While in the herd scenario, we mostly have cooling over northern hemispheric land. But this doesn't yet answer our questions, or doesn't answer the question if those responses are due to reforestation in that area, so the local response that arise due to in situ line atmosphere interactions, or if those changes are from non-local effects, so reforestation somewhere else impacting that region. And so to disentangle those two responses, we use moving window regression, which is commonly used. And the main idea is that we are plotting kind of always for a window, here 9x9 grid cells, the forest versus the temperature changes. And then the y-intercept gives us the non-local effect, and the slope gives us the local effect. And then if we're adding them together, we get the total effect. And so if we do this decomposition for our data, we have the total effect, and then we get the local response. Now, this response is very similar across the three reforestation potentials, which is not very surprising since we're using the same model. And it's showing what is commonly known, that the tropics cool strongly because of evapotranspiration, and in high latitudes we have this warming. But what is interesting is that actually the largest contribution to the total response comes from the non-local effects, except for the tropics. And also those non-local effects really show the largest differences between the three different reforestation potentials. So just by having different reforestation potentials, we can, or just different reforestation locations in general, we can induce a very wide range of non-local effects. And to summarize those biogeophysical responses, we came up with this kind of visualization, which has a lot of information, so I'll guide you through a bit. So the idea is that the color bar here is showing biogeophysical temperature changes. And then for each IPCC land region, we show the reforestation potential by the size of the dot. And then within each dot, you see an inner dot, which shows the local temperature response, and an outer ring, which shows the total response. Now, the idea here is that this will help us to identify regions where reforestation is recommended or rather not. And so some potential combinations are that we have local cooling and total cooling. So that means that our total response is mainly due to the local cooling, such as in Amazonia. And so this is kind of the best possible scenario for reforestation as a climate change mitigation solution, because we have cooling from carbon uptake, and that is further supported by biogeophysical cooling. But what can also happen is that we have local cooling due to reforestation in that region, but actually non-locally, we're impacting that region such that we have a total biogeophysical warming. This is, for instance, the case in East Asia. And so reforestation here would still be beneficial because if this local biogeophysical cooling can either mitigate non-local warming or in the absence of such an effect can provide cooling in addition with the biogeochemical effects. Then we come to a third combination where we have very strong local warming, which is actually the dominant total response. This is kind of the worst possible scenario from a climate point of view, at least for reforestation. Because if we plant trees in these regions, we're actually either it leads directly to warming if the biogeophysical effect is larger than a biogeochemical cooling, or at least it's completely counterbalancing any cooling effects. And this is, for example, the case in Central North America and Siberia. And then a fourth possible combination is kind of that the local response of forests is not very large, but we have a total cooling because of non-local effects. Now, this is great for the region. They're kind of having cooling effects by someone else doing the reforestation, but obviously this is not a very reliable climate strategy. And so if we put all of this together, what we can see is that we really have regions where, especially in the tropics and subtropics, although it's much more pronounced and heterogeneous than that, where we can recommend reforestation from a climate point of view, because the local cooling and the non-local effects are really helping to kind of mitigate global warming. And then there's regions, especially in high latitudes, where reforestation is maybe not the ideal solution because we're actually might enhancing or at least counteracting cooling. And so to summarize, what we basically find is that less can be more. We can achieve very similar net global cooling with significantly less land. I mean, imagining reforesting the whole EU or not, that's a massive amount. We have the latitudinal trade-off, which is well known in literature, that we have kind of the tropical and subtropical cooling because of evapotranspiration, but we give a bit more nuance to that. And sadly, what I should note is that those biogeophysical effects are really rarely considered in policies. They're not included in the Paris Agreement or the UN RED agreements. And so if we want to have reforestation as at least a partial mitigation strategy, those effects have to reach the policy to actually have sensible policies in the end. Although what I also would like to end on with is that this is a massive reforestation we're implementing, and it only offers a cooling of around 1/4 of a degree. So reforestation will only ever support but not replace decarbonization. And if you're interested, we have a preprint out, or you're very welcome to contact me, and I'm happy to hear any questions, although I'm sadly not in person with you there today.
Awesome, Nora. Thanks. Questions for Nora online or in the room? Yeah, go ahead, Abby.
Yeah, thank you so much. I'm curious, how do you know that where the non-local effects come from? So you've got non-local effects, but do you know that the cooling isn't being caused by something in the high latitudes, or that the warming isn't being caused by something in the tropics? Do you have a way of untangling that?
Absolutely. That is one of the issues with the current setup we are having, which is why I'm running additional simulations where I'm just reforesting one region at a time at the moment. Because as you say, we can't tell where those non-local effects are coming from. We can say in this region we have large non-local effects, but where those effects are coming from, we can't tell with the current setup. So I'm kind of rerunning simulations, just reforesting different regions and then looking which one is actually causing the non-local effects.
Other questions? We have a little bit of time in the schedule now. We can kind of open it up more broadly. Try to pick these talks because I thought they would give kind of wide breadth of the types of questions that you can ask with CESM and CLM. And I think it's kind of exciting to see that. I'm also a big kind of the storytelling thing that Laura was talking about. Other folks have either specific questions for participants or other thoughts. Everybody.
Just
go ahead.
It's a question for this last talk, which I really enjoyed. So I missed the setup of your simulations. Are you using ensembles, or otherwise, how are you evaluating the significance of this cooling and warming, given that at the global level you just have a 0.25 type of delta? Thank you.
Yes, we are using 5 ensemble members. I did run additional simulations because I noticed that, well, for temperature, this is absolutely enough to get a significant and robust response. For precipitation, it was not. So we have 5 ensemble members for each simulations in what I just presented. But for precipitation, this is sadly not quite enough to get a robust signal.
Thank you.
I got a question for Kyle on the rain and snow work, which I found really interesting and a good combination of both the large scale, the regional refinement to capturing the AR, as well as the regional refinement for the snow melt. And I'm very curious about how the CLM or CESM calculating the rain and snow energy. And in some specific hydrology models, there will be like energy input from the rainfall, and this will driven multiple snow melt. So how does the CLM presenting this?
Sure. Cool to stay here. Yeah. Thank you for the question. That's a really good one, and one that we've been starting to think about more. And we haven't explored it yet. So unfortunately, I don't have like a very satisfying answer for that right now, but it's something that as I'm learning how land modeling works, like that's something that I've been encouraged to explore. So one thing that I didn't get a chance to mention is with this perturb parameter ensemble, we're starting to consider different metrics that we want to explore, and how are we defining how are we defining accuracy or adequacy, and those kinds of metrics that you're describing are really important, and we want to explore those more in detail. So hopefully in the next couple of months, we'll have more detail on that, but it's something we are interested in exploring. But unfortunately, I don't have an answer concrete right now, but yeah, I appreciate the question.
Thank you.
I might make a stab at what I think you're asking is like if the rain that actually physically hits the snow melts the snow in CLM. Sort of
so like in some model, like like hydrology model, like NOAA or WIC, there will be energy input when the rain falling on the snow will be the rain will having the convection energy, as well as when it is refreezing, having kind of the latent heat release. So that kind of process will largely facilitate the snow melt, especially when there is a thinner layer of snow. I think which will be why the real snow is a very hot topic in the snow melt. So I'm just curious how this process has been represented in the CLM, because I just checked the code. I'm not sure if my understanding is correct. So currently,
I'll make a stab, and I'm happy to be corrected. I'll say this. great confidence and little certainty. That I think the rain just passes right through the snowpack and CLM, and then would get flushed out the bottom. So I don't think there's that interaction with the snow. I don't know. This is why we need a community model, because nobody knows all the answers to these questions. They'll show on the question. But I'm pretty sure that we don't have like that enthalpy flux or that melting in the snow and CLM.
We don't have the enthalpy flux.
There's no other,
but I don't know that they go straight through the snowpack. I think it might turn to snow.
Yeah, or refreeze. Sure.
Yeah, I know different like models, like different snow models having different structure, and this real snow is not widely adopted. But there are many models has already having this. Like if would like to follow or refer a little bit, I believe this will like the heat release into the snowpack will largely influence the snowpack energy, and you might find an even stronger signal in the snow belt under different climate change scenarios. Yeah, I have done some work in this, so that's my impression of doing this, especially real snow is kind of consists of a large amount of flash flood in the Western US. So like that's why many people are very interested in the snow melt energy.
Thank you. Appreciate that.
It was our first proposal idea that somebody
I also have a question for Kyle. So you're making your own perturbed parameter ensemble with atmospheric variables. I'm just curious, like how much, maybe this is also for everybody else, like how much can we leverage all the perturbed parameter ensembles that people are running for people to at least get a starting point for answering a more specific question? Your question might be really specific, but actually these ensembles are kind of general and can be used for a lot of things. And do you have plans for how you might be able to use existing ensembles for your later phases?
Yeah, thank you for that question. I don't know if I'm addressing your question specifically or the right way, but the parameters that we are using right now for the atmosphere is leveraging several existing PPEs. There was one PPE that was done here at NCAR that looked at maybe about 45 or 50 different camp parameters. And the ones that I chose are ones that were shown to be impactful for things like cloud forcings and precipitation. And there have been a few like E3SM PPEs, and I leveraged some of those results as well. So I'm not sure if I'm quite getting at your question, but I think one thing that I definitely want to emphasize is using existing PPE results to have a baseline of like, okay, we know these parameters are likely to be more impactful. And a lot of this is just also trying to be as computationally efficient as possible. And so hopefully leveraging some of these prior PPs could be helpful with that, and to see also what the applicability is. So I'm not sure if I totally answered your question there, but yeah, important to think about.
Like 3 questions for Kyle. One was, what is the innermost domain resolution of your?
So the 16th of a degree, about 7 kilometers.
How much kilometers?
About 7 kilometers.
Okay. So this seems like ripe for a hill slope, because still the snow is going to be totally controlled by elevation, and even at 7 kilometer resolution, slope and elevation. And so I wonder if we could get a configuration that just has the hill slope model running in that inner area, so you're not spending all the resources. So that might be something worth.
I appreciate that.
And the second is I feel like maybe the PPE, I guess you're starting already, but running the land and the atmosphere together rather than running them separately would kind of make more intuitive sense to me, because these things are all going to be interacting. And so probably get a better bang for your buck by just running one PPE with parameters changing in both. Anyway, there's lots of people there, as you already know. Happy to help you try to work on this.
Thanks. Yeah, that's
overall, I think it's a great project. That's exactly the kind of thing we need to be doing. And I'd like to use this as demonstration of CSM impact for sure. But
this may be a follow-up on Gretchen's question, but I feel like many of these impact stories end up being very local, and they almost kind of necessarily are sort of one-offs for particular questions. And I think one of the challenges, and we've talked about this in previous CSM meetings, but like how do we generalize our science so that it's easier for people to do kind of impact studies like what Kyle's doing without this like really exhaustive, like pre-work that you're doing. It's like you have a couple of years worth of work to tell the story. I don't know what the trick is.
Can I comment on that? I mean, I think existing databases of these PPEs lets you do it faster, right? If you can go and explore a data set and figure out, oh, this is what's going to make a version that's going to work better for my specific question. I don't know how you do that in the sense of, variable resolution that are focused on different regions, but it probably is something that's going to have, if you figure out what's working in this mountainous Western domain, it's probably going to apply to other mountainous Western US domains as well. I just think there's a lot of data there that we could use to learn too.
Other questions or comments, or people are ready for a bio break? All right, well, we're at our break. There's a men's bathroom kind of down that way, a women's bathroom down that way, and gender everyone bathroom upstairs. There's about half an hour for the break to come back in.
Okay, welcome back, everyone. The second session is very crop themed, so get in the crop mindset here. Our first presenter is going to be remote, and this is Ruparti. You can go ahead and take it away. Thanks.
Yeah, thanks. Hi, this is Ruparti. I hope the screen is visible, like in full screen mode.
Good.
Yeah. Okay. So I am doing currently postdoc at Luxembourg Institute of Science and Technology. So we started, our objective is to calibrate actually the crop module of the CTSM framework. And we started with the crop rice. So first I will start with how we set up the model in one particular location and how we developed a framework to calibrate the parameters with the parameter sensitivity analysis and PPE experiments and the multi-objective optimization. And then how we plan to move ahead to get a global optimal configuration. So to start with, I will first describe the methodological framework we adopted. We set up the model in a location in a point scale mode in Vercelli region of Italy. And we started with the crop rice, and we used the atmospheric forcing dataset as we are using it like standalone mode. And so we used ERA5 reanalysis data for atmospheric forcing. And we did two-step spin-up procedure to get the equilibrium. And then we tried with different management practices with and without irrigation, with and without fertilization. So we first did the simulations with the default parameterization. Then we went for the calibration framework. First, we did the sensitivity analysis, that is one at a time. We perturbed all the parameters with plus minus 20% perturbation. And then we got a subset of the most sensitive parameters. And then we went with the perturbed parameter ensemble. So we perturbed jointly the most sensitive parameters, and we got the 100 ensemble members. Then we figured out that actually the base configuration is varying across all the output variables, and it is also varying across time scale when we are integrating those output variables at different time scales. So then we needed to get one optimal solution using the multi-objective optimization framework. So this was our framework, and first I will show the results. That is yield with different management practices. So we first we run it without irrigation, and then with and without fertilization. And the gray one is the observed yield data set. We retrieved it from the ISTAT database for Italy. But then we did the parameter sensitivity analysis. And now we can see that the parameter sensitivity is actually varying across different management scenarios. So the most sensitive parameter what we got for the irrigated condition is actually a little bit different what we got in rain-fed condition. In rain-fed condition, we can see that the plant hydraulics related parameter are getting actually being important, which is not the case in case of irrigated condition. So we here narrowed down the most sensitive parameters based on the parameter effect, the metric to determine the sensitivity. And then we jointly perturbed those 20 most sensitive parameter. And then we went with the PPE framework. So we got now the 100 ensemble member. Here I have plotted for GPP. I run the model at hourly time scale, and we can see the diurnal variation of the GPP, the simulated one, the observed one. The observed GPP data we retrieved from the FluxNet data that is actually located in the Po Valley, that is a rice field in the region of Italy. And we tried to validate the model-based simulation with the observed dataset. So here we identified the best matched ensemble member for each month. So we can see actually the best matched ensemble member is actually varying across months. And here we can also observe the phenological evaluation. Here I started I modified the planting date. I started it from the month of March to make it align what is actually happening in the real field in case of Italy. So we can see that we can clearly see the phenological evaluation started to begin in the month of April, and we can see the harvest is actually in the month of October. Now this is for yield. So yield data we have estimated on annual scale. And when here also we can see that the best configuration from what we are getting from all the ensemble members is actually varying annually. So the best configuration, the best set of parameters are actually varying monthly and annually and across different objective variables. So we needed to formulate one optimization framework. Here we did the Pareto optimization, and we defined 3 objectives, that is based on GPP, LAI, and yield. We constrained the model simulated variable with the observed data set, which are actually integrated at different time scale. And then we got one optimal solution. Then we run the model again with the optimal set of configuration, and that is the calibrated one. Here I have plotted. Then I tried to match it with try to validate it against the observed database, and we can see there is actually the aggregated error being reduced in case of calibrated one. So this is with the yield. And similarly, in case of leaf area index, we used the MODIS LAI variable. And similarly for the GPP, that is the diurnal variation, we can see the results from the calibrated setup. So to summarize, we observed the sensitivity of the parameters, which is actually varying across management scenarios and which is varying across variables. And when the variables are integrated at different time scales, we are getting different optimal configurations. So to address that, we formulate one multi-objective optimization framework, and we got one optimal solution that is for Italy. Now we plan to apply this framework for different location across different climate zone to see to consider the spatial variability as well. And the objective is to find one global optimal configuration and to compare with the local configuration, how it is varying across different climate zones, and to build a robust framework for calibration. So thanks. Yeah. Great, thank you. We have a few minutes for questions. And if you're online, feel free to raise your hand.
Yeah, sure.
Yeah, Sam, go ahead.
Hi, this is Sam Raven. I'm a software engineer and I work on the crop model. This is really, really cool. I wish Will had scheduled me before you because my method is a lot more manual. But anyway, I'm really happy to see this. I'm wondering, so was sowing gate or like the sowing window one of the parameters that you looked at?
Yeah. So sowing date, we try to align it what is happening actually in real field in Italy. So in Italy, the planting date, it usually starts in the month of early April. So we try to align with that.
Of course, yeah, okay. Said that.
Yeah.
Any other questions? Yeah, Will?
I'm curious if your kind of long-term goals are to come up with a kind of a universal rice parameterization, or if you feel like it'll be kind of idiosyncratic based on all these different climate regions and varieties that you're trying to grow.
Yeah. So we started with rice, and once the framework is finalized, maybe we can apply for other crops as well. And the goal is to target different climate zones and get one global set of configuration.
Yeah, please be in touch as your work matures.
Hi, this is Danica Lombardazzi, and I also work on the crop model in CLM. I guess one thing that I'm curious about is a lot of these flux towers have differential management, so they might have crop rotations or other things, and I'm curious if you have accounted for that in some capacity when you're doing your parameter estimation.
So we were we plan to consider different, the flux tower data, of course, based on the FluxNet database. And it is also there should be some uncertainty. Is it I'm answering it in the right way, or I got your question, or?
I think that's part of it, but the other piece that I was curious about is, when I've tried to simulate crops at flux towers, I've encountered the fact that you might have a flux tower that is planting rice, but only every other year.
Okay. Yeah. I got your point. But when I retrieved the data actually from the flux tower sites, so there is some inconsistency in case of the year, like the time frame. So for some cases, it is available like for 2 years. In some location, it is for like 8 years. So yes, there is some inconsistency if we consider across region. So the goal is to develop a framework where we can, if we consider different time period at different region, so what will be the case? But I tried to find out the locations where is actually rice field and the FluxNet data actually for rice field.
Great. Okay, thank you. I think we'll transition now to an in-person talk. Will, you're up next.
Sorry. I almost took Will's badge today.
Great, thanks.
I'm Will Selvage. I'm from Colorado State University, and today I'll be going over the development of crop ozone functions within the community land model. So as a little bit of an introduction, we know that there's layers of ozone in the atmosphere. The stratosphere is the layer that we normally think of, and this is the one that protects us from all the harmful sun rays. The lower layer of ozone is in the troposphere, and it's often referred to as surface level ozone. This is what the talk focuses on today. So surface level ozone is created through atmospheric interactions. Nitric oxides and volatile organic compounds are released into the atmosphere through fuel emissions. These compounds then react with sunlight to produce the surface level ozone. It is harmful to plants and humans, and there is high regional variability in surface level ozone concentrations in today's world. When thinking about ozone in plants, it travels through the stomata and enters into the plant leaf. Once it's there, it damages photosynthesis cells, and this leaves visible damage on the surface of the plant leaf, such as here, here, and here. The surface level ozone also impacts plant transpirational processes. However, these impacts vary widely across plants. So we know that ozone impacts plants, so many researchers wanted to know how it impacted our crops and specific crops. These researchers then took physiological measurements of impacted ozone plants and reported their photosynthesis, transpiration, and yield changes. These are then oftentimes put into a synthesized crop data set and implemented into land models such as the community land model. This is all in an effort to improve the ozone crop damage representation, understand our global water and carbon cycles better. The synthesized crop representation has problems though, as it often has muted impacts due to high variability in different crop types, ozone exposures, and ways that conductance measurements are taken. It also represents one overall crop damage function, which we know that different crops are impacted differently to ozone exposure. This study specifically focuses on specific crop representation within the community land model and developing ways that we can represent ozone damage. When thinking about our data, we combined two data sets for a total of 57 separate studies over 600 data points spanning the years from 1971 to 2022. We had crops that include wheat, rice, soybean, corn, and cotton. In an effort to try and control the variability in these studies, we took previous collections of exposure systems, rooting environments, and control air types to see if any of these could explain the results and variability that we're seeing in response functions. We also decided to add leaf age in this study. That is because the newer leaves have less accumulated ozone damage and might not be as impacted compared to older leaves on the plant. We also wanted to look at plant stage in order to identify if there were certain times in the crop cycle that were more impacted or more vulnerable to ozone exposure. For our simulations, we ran crops of wheat, rice, and soybean. This is because these are studies with over 3 individual studies that report them. We then developed response functions using linear models to separate ozone exposure metrics. This includes our crop dose and our exposure metric CEO. CEO is simply the exposure around the plant, it's the ambient concentration, and does not take into consideration how much ozone is getting into the plant. Well, the crop dose response function does, and it is controlled by a stomatal conductance measurement. We also ran a generic crop dose function. This is the ozone damage response function that is currently in the community land model. However, it is a generic synthesized crop response function and does not specify individual damages. It is calculated in the same way that crop dose is. We ran low damage and high damage simulations, where the low damage was a mean monthly ozone exposure, and high damage simulations at a fixed 80 parts per billion. This results in 3 crops with 3 differing functions at both low and high damages. It's important to understand the response functions that were developed to help identify the results that we have. For the generic dose I show here, which is already implemented into the community land model, photosynthesis has a negative slope and stomatal conductance has a step function that is applied. In the development of the crop dose response function, we notice that wheat is entirely positive. However, we do not see significance for both photosynthesis and stomatal conductance. Rice is positive and negative for photosynthesis and conductance respectively, but no significance. And we have a negative soybean interaction with both. For our exposure metric, we see a change in the wheat photosynthesis slope, which becomes significant at a negative value, and conductance stays positive but is no longer significant. Rice stays the same, and soybean now has 2 significant response functions. The table on the right here is just a reminder of those response functions as we move through simulations and trying to understand what we see in our results. Here, I'm showing the mean GPP for the simulations, and we see that at the low damage simulations, our response functions do not vary widely, and we do see a decrease in GPP. However, for the high damage simulations, we see an increase in GPP compared to the low, and there's a little more variability within each response function. It's also important to note that the control and low damage simulations go to 0 GPP and after June, while the high damage simulations continue producing high GPP. For rice, we see limited variability within the response functions, as well as a slight decrease in both the low and high damage simulations. For soybean, we see that there are small variabilities within the response functions, as well as a slight change in the growing season here, where the slope, or I guess the line, slightly decreases in the high damage simulations compared to the control and low. When looking at transpiration, the first thing you'll notice is that we have higher than control transpiration for wheat. This could be due to the response functions laid out earlier. We also, for rice, we see that there's limited response function variability as well, but we do see a larger reduction in transpiration at high damages. For soybean, we see a slight change in the growing season here as well as limited variability between each response function. Moving on onto grain yield, this is a plot showing the average monthly grain output. Our low damage simulations show a reduction in grain output with limited variability within the response functions. However, our high damage simulations show an increased output of grain yield for our new developed response functions. You'll also notice that the peak of grain yield is different, where the control and low damage simulations peak in June compared to July for the high damage simulations. Again, I mentioned the variability earlier. With the crop generic dose response function, we do see a decrease in the high damage simulations. However, there is also a larger output in August compared to the new developed response functions. For rice, we see that the control and low damage simulations both show a reduced yield. There's limited variability within each response function, and the control or the low and high damage simulations are relatively similar in the reduction of yield. For soybean, we notice that the peaks are at the same time. However, we have a slightly larger output of yield in September for soybean in the high damage simulations compared to the control and low. So now we have to ask, why are we seeing increased productivity in some of these crops during high damage simulations? Is it a product of our response functions, or is it simply a model impact or model feedback that is causing this to occur? I am going to focus in on wheat because it shows this most clearly. To understand this, we have to first understand the transition from the crop leaf emergence stage to the grain fill stage. In order for crops to do this, it can go to the grain fill stage in two ways, either reaching the required growing degree days, which is an accumulated 2-meter air temperature after the leaf emergence stage. It can also transition into grain fill by reaching the crop maximum total leaf area index. When looking at wheat simulations here, we notice that the high damage simulations result in a higher total leaf area index in June. We then see a reduction in soil temperatures, which is likely due to increased shading from the more leaf area. We also know that the plants are transpiring more in these high damage simulations. And the higher leaf area index, along with our positive response functions, are increasing that transpiration. The increased transpiration results in more evaporative cooling of the 2-meter air temperatures. This reduces the accumulated growing degree days, which lengthens the growing season. This results in higher total GPP, transpiration, total leaf area index, and yield. It is also important to note that these feedbacks can loop into each other, where a decreased soil temperature and air temperature might allow for more productivity in the plant. So in conclusion, our different ozone predictors do not appear to improve, predicting physiological crop damage to ozone exposure. We did not see a lot of variability within each individual response function. However, this is still an ongoing process, and looking further into this, especially during the high damage simulations, is important. The individual crops do show variability in the responses within CLM, and this represents the need to develop our individual crop response functions to better model our global agricultural systems as well as carbon and water cycles. And it's still a work in progress. There's a lot more work to be done on this. But with that, I'll end it.
Please, we have a few minutes for questions.
That's super interesting. I don't know a lot about what actually happens with ozone damage. Is it reasonable that photosynthesis would increase? Like, why would photosynthesis in LAI go up?
Yeah, there are various studies that show that photosynthesis can increase. However, most studies would agree that it generally decreases. Something that could be leading to that is increased transpiration, and just if the plant is transpiring more, it might force the plant to increase the photosynthesis. I would also say that our response functions in general were relatively flat lines, and that's actually why you see the wheat photosynthesis slope flip, where it was positive and then it's negative with an exposure. It's just because all of the responses are super minimal in their slope.
Yeah, interesting work. I'm just curious of, in the earlier slides, you show limited response, even under high damage, limited response to photosynthesis. But later, for the same simulation scenario, there's a huge response to yield. So that means the ozone damage is more not through photosynthesis, but through other process like related to harvest index. So yeah, because in the earlier slides you show limited response under high damage scenario to photosynthesis, but later I see like huge response to yield. So under high damage, so I wonder how the ozone impact. It is probably not through photosynthesis, from other processes related to harvest index. So yeah. I'm just curious, like if you can clarify what really happened there.
I think it's likely due to the increased growing season. The plants are given more time to photosynthesize and gain higher leaf area because of the growing degree day shift. That's why we see higher yields in specifically wheat, where the growing degree days are lower. And so we have this shift that allows the plant to stay in that leaf emergence stage and get ready for the grain fill stage in a, I guess, more robust manner.
And then while we transition to Sam's talk, there's a question in the chat.
Yanshu asks, can we eventually predict the crop yield loss due to ozone damage?
Yeah, a lot of studies have done that work where depending on the ozone damage, we see reductions between, I believe it's like 5 and 20% based on 50 parts per billion exposure. So a lot of work has been done in that, and I think developing the response functions will help.
Okay, great. Thanks, Will. I'm going to emphasize 2 questions. All right, hand over to Sam to talk about the new crop model updates.
Yeah, thanks. Thanks everyone for being here. If you saw my talk at AGU, feel free to check your emails. This is going to be almost the exact same thing. Right. So in CLM 5.3, which I think we released in 2023 or 2024, we made some pretty big changes to how growing seasons work in the model. Previously, so we changed two major things. One is the crop sowing window, and previously that was just a per hemisphere window. So all rice in the northern hemisphere would get planted between these 2 dates, and same for the southern hemisphere. We also had these maturity requirements, which are in units of growing degree days, which I think the previous 2 presentations both talked about. And those were global parameters for each crop, adjusted a little bit based on recent climate in the grid cell. But basically what that means is how warm does it have to be for how long for the crop to reach maturity? And if you have more leaves, it cools things. And so that results in a longer season, like we saw in the last talk. In CLM 5.3, we changed these with the crop sowing window is now based on per grid cell planting dates that come from the Global Gridded Crop Model Initiative. Jonas Jägermeyer did hero's work to get, typical sowing dates for every crop around the world. And so now we're centering our sowing window on that date. And then for the maturity requirements, those are now per grid cell parameters, again, based on the length of the growing season and when in the year the growing season is, as well as what climate forcing we're putting through the model. And again, those get adjusted based on recent grid cell climate. So if it's been very warm over the past 20 years, it'll be warmer, or the PDDs will be higher than what's required in the actual input file. And so if you read the 2023 paper, you saw that it improved yield performance for some crops and it made others a lot worse. And so I said, well, we're going to need to reparameterize, and this is the work that I'm presenting now. So this effort proceeded with a strategy aiming to minimize yield bias in 1995 to 2005. And the reason for that is that the GGCMI seasons are ostensibly for the year 2000. So seasons are going to shift in real life as you get farther away from that. So we're focusing on minimizing yield bias there. I'm looking at just yield because it's something that we have a global data set for. And it's also a really important parameter or output, but ideally, eventually we'd like to expand. We're also hoping to get a realistic variance throughout the time series. We want to minimize failed seasons, which I define as seasons where the crop gets harvested, not just before it's reached maturity, but well before it's reached maturity. And the specific threshold of that is based on rules from GGCMI. But for most crops, they have to reach 95% of their growing degree day requirement. And this isn't really a strategy, it's just something to keep in mind. We expect that global trends in yield will be less steep in the model than what they are in the observations. So between like 1960 and now, things have improved a lot due to expanding use of in advance of technology. So that would be like mechanization, expanded use of pesticides and herbicides, things that we don't represent in the model. So we're not going to get as steep of an increase. Here, I'll be presenting the results from this work that proceeded from 1 degree runs, so the FO9
resolution. I did 4 runs. First was the original crop calendars with the GSW3 climate. These are all using the same CLM version, by the way. So it's a post 5.3 version, but using the original calendars. And then a run with the new calendars, then a run with the new calendars, but the Crugiere climate, which is what we're using for CLM 5.4 and beyond, I think. Yeah. And then finally, a version with the new calendars, the new climate, and the new parameters from the parameterization work. These colors will be used throughout the presentation, but hopefully I have legends so you don't have to remember. Notes on the figures, when I show yield, I've set yield for harvests that were too immature to 0, with the assumption being that these are things that a farmer could not even market the crop for. Then I'll be comparing to the FAO EarthStat yield data, which if you're familiar with both of these, it basically takes the FAO trend and applies the EarthStat spatial distribution. So we have a time series from 1961 to the present, but with a spatial distribution. And because of that, I'll be taking CLM results and applying them as if we had simulated with the FAO EarthStat area. So if CLM only has 15 hectares of something in a grid cell, but FAO EarthStat has 1,500, I'll take CLM's yield and multiply it by 1,500 hectares to get production. All right, so getting into the results, this is essentially what we had in the 2023 paper, just with the new CLM version. As before, as in that paper, some of the crops improved. Okay, sorry, yeah. And then, so that was the original, and then this is with the new crop calendars. Some of them improved, some were worse, some were neutral. So corn, cotton, soybean, and sugarcane generally got better. Soybean didn't really change bias, but its variance is a lot more realistic, so that's nice. Wheat had now has a worse overestimate, and rice went from an underestimate to an overestimate. All right, so the next step is apply the Crugiere climate forcings. Again, we get mixed changes. Some are better, some are worse. Not going to dwell on this too long, because the real interesting thing is, okay, now what about with the reparameterized crops? Yeah, so the strategy here was I considered reverting allocation changes that took place during the CLM 5.0 parameterization. I compared the allocation parameters to the literature, and I considered changing max growing season length. So those are kind of the 3 levers that I worked with. And in doing so, all of them were improved. And so rather than just having you stare at this, I'll dig into a few of the crops that are particularly interesting. So rice is one of the biggest winners here. We have many fewer premature harvests now with the new crop calendars. So the y-axis here is the fraction of prematurely harvested rice area around the world. And you can see throughout the time series, it was like 30 to 40% of rice area every single year was too immature to actually be marketable, according to our definitions. Applying the new crop calendars reduced that, but it's still really high. You wouldn't expect, if a farmer actually had something that failed 7% of the time, they'd probably go to something more stable, right? And so we are hoping for our results here to result in a crop that fails very across a very small fraction of the global area on average. And you can see we do get that. It's pretty small already for the Crugiere once we have the climate, the new calendars and the new climate. And so we can see where was rice failing? Well, it was failing across China, which is less than ideal because that's obviously a pretty important producer of rice. And so this was the original map where yellow is, it fails every single season in this like 50 years. And now most basically never see a failed season. Most grid cells never see a field season, so that's good. But of course, that boosted our yields pretty dramatically, becoming a worse overestimate than the underestimate it was. And so during the CLM5 parameterization, we had decreased root allocation and expanded the reproductive phase with the goal of trying to get a decent global yield. Not having had the opportunity to figure out a realistic growing season because these global maps of growing season didn't exist before. But now we have that, we can undo those changes, and that's what I did. And so here's what that looks like in terms of an allocation time series. So this is in a theoretical season. The x-axis is representing fraction to maturity. So how many growing degree days have been accumulated as opposed to as a fraction of what's required, where 0 is planting and 1 is maturity. And then I'm going to be showing different colored lines for the different pools that get allocated to. So stem, root, reproductive organ. Y-axis 0 to 1 is the fraction of net primary productivity going to that pool. So this was before with the original parameterization, and this is after. And the main thing to look at here is the reproductive phase starts a lot later, and it also reaches its maximum a lot later. And so that'll decrease yield. And we ended up pretty close to observations. And again, we're mainly focusing on this period, 95 to 2005. So it's especially good in that part. And just as an illustration, we have a less steep trend line. Again, we can explain that by saying those are exogenous technology advancements that we're not representing. Another example, temperate soybean. We also have less prematurely harvested area, just like we did with rice. So originally it was here, using the new calendars got us there, and then Crugiere got us there. But it resulted in a better variance, not so much bias. So you can see it's more or less along the same kind of mean, but the variance is a lot more realistic. But it's still too low in the period that we care about. And so what I did was increase maximum growing season length from 150 days to 180 days, which is much more realistic in certain parts of the world. And I also made it so that the switch of allocation from stem to grain happens faster. So it happens, we'll see. It's faster and or earlier, I'm not sure. All right, so this is the allocation with the original parameters. And again, here is our line for allocation to the reproductive organ. And with the new parameters, that happens earlier, maybe a little bit faster too. And so you have a much longer period where you're allocating all your NPP, or sorry, the maximum amount of NPP allowed to reproductive organ. And that results in a big boost in yield, and now we're looking good for a period of interest. The last thing is sugarcane. It was already looking pretty good. Sam, are you going to touch it? Well, we only had a maximum growing season of 300 days, whereas in a lot of the world, it's in the ground year round, and it's actually perennial in some places, or like a 2 or 3 year crop. So I didn't like having 2+ months where nothing was planted. So I wanted to make it more realistic there. I chose 360 just because things start to get weird when you get close to the planting date. So I just said 360 days. I also increased the allocation to roots closer to what we had in before CLM5. And this is based on some parameterization that was done in the AppSim model. And the reason I thought to do this was because the first thing I tried was just boosting this, and that ended up getting us way too high in terms of the yield. So then I thought to look at allocation and saw roots may be unrealistic. So before, and here I'm highlighting the allocation to roots, and after. So we're getting a much higher peak of allocation to roots, and it's higher throughout. And you can see this results in a lower allocation to reproductive organ during the reproductive phase. And it maybe made yield a little bit worse, but it's acceptable to me to get a much more realistic growing season. All right, so to conclude, the new calendars and parameters in CLM5 improved global yields. For next steps, I guess this is already done. I didn't take it into my take it out of my presentation from AGU, but seems like impacts on the atmosphere coupled model are okay. They're acceptable. We didn't have to revert anything. I'd like to eventually dig more into the seasons that actually get realized in the model, rather than saying, all right, here's your sowing window and here's how long you're allowed to grow into. I'd like to know, is it actually realistic how long this model is actually simulating the seasons? And yeah, I'd like to do a much more systematic ML-powered parameterization, looking at target outputs other than just yield. But for the purposes of exigency, we had to just do this kind of manual one target optimization. Thank you.
We have time for maybe one question.
Great, yeah, let's go online. Rosie, go ahead.
Hey, thanks, Sam. I guess I'm thinking about, this is going to be a predictable question. I'm thinking about all this work that you've done. How hard do you think it is to port this into Fate in terms of like how integrated this code is within the sort of big leaf model code base versus how much it's kind of modularized and sort of standalone? What's your perspective?
So the crop phenology code, I think, is pretty modular and could be ported to Fates somewhat easily. And that's really what I'm most familiar with. The crop physiology, the special photosynthesis, the special allocation. I'm less familiar with that code, and so I can't really say for sure.
It doesn't have special photosynthesis, but allocation it does.
Okay, allocation at least might be tricky.
All right, great. Thanks, Sam. We're going to transition now. And Will's going to give us our CLM overview talk. Thanks, Will.
Great, thanks. Yeah, get ready. Here we go. So I'm super excited that the CLM6 release actually feels imminent now. And as much as possible, I'd like this meeting to feel kind of like an exploration and a celebration of the kind of the journey that we have ahead. We've seen a lot already, that CESM2 has been a really productive, useful model for the science that the working group's doing. And I'd like CLM6 and CESM3 to kind of to fill that same role. And so as much as possible, I'd like this meeting to kind of feel like this bike ride did for Anya. She's almost 20 now. But kind of optimistic and forward thinking. In reality, this is sort of how I'm feeling right now. And it's just kind of more, I guess, a reality of what this season looks like. This is a couple of weeks ago up at Steamboat. Chairlift stopped, and that's what we were looking at. And so I think there are some kind of rocky roads ahead, and I want to acknowledge that, especially folks at NCAR are feeling the stress both of trying to get CSM3 out the door and the kind of more existential threat that we're facing. I don't want to dwell on those. I don't have a lot of new information other than what you've already been reading in the press and on NSF's website. But I just want to acknowledge that that's something that many of us are facing. Okay, I think one of the celebrations, this is both a rocky road and a celebration maybe, is the Slater Award. So for those of you who knew Drew and can appreciate the kind of energy and enthusiasm that he brought to the Land Model Working Group. And since 2018, we've been fortunate enough to offer an award to graduate students and postdocs that make meaningful contributions to the working group for their creative applications of the model, significant model development activities, identifying and addressing major issues, biases, and gaps in CTSM, and then also just having a high level of engagement with the working group. So the list of recipients is getting longer and longer, which is fun to see. Danny was our winner last year for the work that he put into the new dust model that's in CESM3 now. And it's also a real pleasure to see a lot of these people coming back to working group meetings year after year, starting their labs, getting staff scientist positions in various capacities. And it's I think a really nice thing that the working group's able to do. So thanks to those of you who are here that continue to be involved, and also just a shout out to the graduate students and postdocs who really do a lot of the work that we get to share. A couple other announcements. This is kind of, I guess, in the optimistic vein. The CSM workshop is still scheduled, and we're planning on talking about our science June 15th to 17th. The tutorial then is the first full week of July, so the 6th through the 10th. And then I'm planning a CLM tutorial right now. It's scheduled for the week of November 16th, which is a little later than I wanted, but between scheduling conflicts here and Sam Levis's availability, because I want Sam to be able to be here. That's where we've kind of landed on. So that's the week right before Thanksgiving. Put it on your calendar now, and hopefully we'll have some more details for what that'll look like. It's been, I think, since 2019 when we did the last full CLM tutorial, and we have a lot of questions for you, Donica. Anyway, so those are kind of some upcoming events I wanted to note, put on people's agenda. So another big win that we've had is the CTSM 5.4 release that came out kind of early December. There's a ton of new things that went into that. So the new surface data sets, which are compliant or kind of representative of CMIP7 data through the historical period. And then Dave just sent an email today that a few of the future scenarios for CMIP7 are now out, at least for land use change. So we'll have those hopefully coming on board soon. Another big change is that Crew JRA is the new default. We've been using it for a while, but now that's the default data atmosphere product that we'll be providing. We'll still have GSWP3 for folks who want to use that. But Crew JRA offers some advantages, the biggest one being that it goes through, the version that we have goes through 2023. And it's the data atmosphere model that's used for the trendy simulation. So we're kind of going to now be calibrating towards what we're doing in trendy. And then I have photos of the software engineering team put up on the bottom because we couldn't have done this. This wouldn't have happened without that team. So I really appreciate the energy and expertise of Eric, Sam, Adriana, Sam, Keith. This is Keith, if you don't know what Keith looks like. He's hard to find a photo of online, as well as the Fates team and folks at NORISM. So yeah, it's a huge effort to get this out. I think these slides will be made available after the presentation, and there's a link here, but you can also find it on the GitHub website for what's new. And so we this new feature for the minor version model releases tries to summarize everything that's new in CTSM 5.4 compared to the previous minor release version, which was CTSM 5.3. And so we try to kind of keep on top of what the latest things are. I also want to highlight, so this release came out December 10th. And since then, the software engineering team has made over 20 tags, which is about 2 per week over the holidays, and just like a huge amount of work that's gone in. And so what I want to do over the next few minutes is summarize what's come in a lot of those most recent tags. And the biggest thing I want to highlight is that Linnea and the rest of the PPE team, so Katie and Daniel and Dave have really put together a solid carbon cycle. And what's shown here is in 2 versions of the CTSM 5.4 and the post 5.4 release. So this tag that's called 124 and another one that's called 131. These numbers are just representative of the issue number on the LMWG dev webpage that I use to keep track of the simulations we're doing. It doesn't really matter a whole lot more beyond that. And so one of the targets that Linnea is calibrating to is GPP, and she's trying to hit this target of, roughly 125 petagrams of GPP around the year 2020. I'm being approximate here. She can tell you the details, but they're kind of shaded area. And so we've got 2 versions of the model that sort of nail this target. You can see that on the ILAM scores here. So GPP is purple, which is better compared to CLM5, of course, with GSWP3 climate. So we're doing better in terms of GPP. And the other 2 targets that she was targeting were biomass and oops. Gave away the punchline there. So biomass and leaf area index, those are both looking better than CLM5 was for the data atmosphere that it was calibrated to. So I want to emphasize that like we're doing a really, really good job. The biggest thing that happened in this 131 target was we had too much soil carbon. And so we dialed that down to get a better soil carbon number here. Okay, so then we put this calibration, threw it upstairs to Cecile, who's doing a lot of the coupled model runs. The blue line here is the exact same as what it was in the last runs, but when you run with the CESM3 climate over this historical simulation that Cecile did kind of around AGU and Christmas, our carbon cycle doesn't look nearly as good as the target. And the other thing that we noticed is not only is GPP pretty low, but our fire is really high. And so one of the things that the kind of features of CESM3 that we want to be able to maintain, or that we want to kind of highlight, are these emissions-driven scenarios, which, having low GPP isn't the end of the world because the trend looks okay. But then also potentially having interactive fires. And we're going from a GFED 5 observation, which is around 800 million hectares per year of fire in present day. The I case was kind of well calibrated around 700 million hectares, but the B case, the coupled model case, has way too much burned area. A lot of that's in savanna regions, especially in South America. And then I also want to just highlight that we're getting much lower burned area in boreal regions in the coupled model than we did before. I think that low burned area in Arctic and boreal regions is probably going to be persistent in CESM3. There's too much snow that melts too late and it's too wet. So those are hard environments to burn. Whereas the savanna regions are much more arid. They're hotter, they're warmer and drier. And so it's not surprising that CESM3 has a higher burned area. So these are the two biases that we're now trying to address. The first two of these are tuning parameters that we're doing everywhere all the time. So we're suggesting that we change tropical evergreen forest to decrease Medland slope, which will increase evapotranspiration in LAI. And in boreal evergreen forests, we're also trying to increase LAI and GPP. So those are on the new default parameter file that's being used in both I and B cases. So, the default parameter file. But for fire, because of these like idiosyncratic and regional climate differences, what we're suggesting is that we have a different land tuning mode, which is something that we did in CSM2 for CLM6 coupled with CAM7 that will reduce the global burned area. So to look at what that looks like, these are now I cases. So plugging these new parameters in. So B, this is for better or worse, B is always baseline, the colors change. So this is the kind of released version of CLM 4.5. And now with these new parameters where we've changed the PFT calibrations for tropical evergreen forests and boreal forests, you can see that we're getting higher GPP, which is as intended, and it's kind of happening in the right places. So this is the absolute change. So you see, light green areas across boreal forests and in the tropics. The percent differences look a little bit stronger, and the map looks reasonable to me. The other thing I want to say is that these are all run with diagnostics through the land diagnostics framework. And so those of you who are sticking around for the tutorial on Thursday, these are the kind of plots that we're able to make relatively easily now. So that's an exciting feature to update our diagnostics package. Okay, so I guess what I want to highlight here is we're going from a little, roughly 100 petagrams carbon GPP in the pre-industrial to about 110. So this is kind of 10 petagram increase of GPP in the I case. And then when you put that into the B case, you also get about a 10 petagram update. So the historical runs that Cecile did around Christmas had started around 85 petagrams carbon. Now we're up to 95. So it's not quite what we were for the release version of 4.5, but we're getting close. But there is this kind of, I don't know if you want to call it a degradation or not, but it's an increase in GPP, both in the B case and the I case, relative to this observational target that we were hitting. For burned area, Feng Li suggested a couple different flavors of parameter changes, and then Sam Levis did a bunch of experiments kind of testing these out in a B case sandbox. And we are able to, with both parameter suggestions that Fong made. We were kind of reduced burned area in ways that look better. There's still too much burned area in South American savannas. And what I think is interesting here is that in the old version, which is the blue line where we have high burned area in these savanna regions, we're decreasing the burned area. So that's as intended, and that's increasing LAI in ways that are positive. Again, these are these are present day. So we're kind of underestimating LAI in the B case, but in ways that are, at least we're moving in the right direction with this change to the parameter set. Okay, so I had really hoped that I'd be able to run ILAM with these cases, but it kept failing yesterday, and this is as far as I got. So you'll just have to trust me that the ILAM scores are not going to look quite as good in this latest calibrated version of the model compared to what we were getting in 131. And that's kind of by design. We like to get a better B case. We're necessarily increasing GPP above our targets. LAI, I'd say the LAI products, none of us have a ton of faith in them, but we're going to degrade the ILAM scores, and then biomass, I think we'll be okay, especially compared to where we were in CLM5. We are going to have we're introducing a more robust carbon cycle into the land-only modes with our target, with the aim of improving the model results in the coupled model. And you can look at some of the LDF results, which are just case-by-case comparisons for these 2-degree cases that are up online. So huge thanks to Linea for kind of in short time. I came back from Christmas being like, we're going to start spinning up CLM or CSM3. And it turns out we had a ton of bugs that on the land side to fix and many other problems. But Linea, Fong, and Sam were really critical in addressing these problems as well as others. So thank you. But I also want to emphasize that the Land Model Working Group provides more than a well-calibrated carbon cycle model. A lot of what we hear about is calibration and carbon cycle, and I, of all people, am saying this, that we offer a lot more than a robust biogeochemical model. And so one of those things that we offer is FATES, and we'll get to hear a lot more tomorrow and Thursday from folks that are working on FATES development. And I think that's one of the exciting things moving forward that as a working group we need to really emphasize is pivoting from what I call the big leaf model to FATES. We heard already this morning about advances in the crop model. And then we'll also hear tomorrow about some of the work that Sean's doing with hill slope hydrology. And I think that's also a really exciting path forward that we'll get to think about. And then also tomorrow there will be some urban model talks, and CSM3. CSM2 was one of, or maybe the only model with the CMIP class model with urban in it, and CSM3 will now have transient urban capabilities, which are pretty exciting. I put a little asterisk next to FATES and hill slope hydrology because those aren't on by default in the CMIP runs that we'll do, but those will be supported configurations that we have for the CSM3 release. So in land only, for the CLM6 release. So in land only runs, we'll have supported FATES SP and no comp biogeochemistry cases that Adriana is working on now and that we'll talk about tomorrow, as well as some hill slope hydrology configurations that people can work with. So beyond these kind of big picture features that we have, we're offering many more point scale capabilities, and we'll also hear some more talks about neon and plumber sites over the next few days. We already heard some single point talks already. And in those single point configurations, it lets you turn on some, I think, nice features. And so Gordon will talk about the multi-layer canopy model and others that are interested in thinking about multi-layer canopies. And right now that model only works in point scale runs. And then we'll also hear some about Mimics. And so Mimics is a soil biogeochemical model that can be flipped on with a nameless change in CLM. And me and Katie, and I guess that's it. We'll present some Mimics work that folks are doing. The working group also is providing a bunch of post-processing capabilities. So this is again a nod to the tutorial that we're doing on Thursday. But all of this is wrapped up in Cupid. And so Mike Levy, who's is the Cupid lead now, is graciously going to come and lead that tutorial. I've been working a bunch on developing some LDF capabilities. And so the things that you don't like about LDF, which is the Land Model Working Group Diagnostics Framework, which is shamelessly built on ADF, which is what the CAM group built for atmospheric diagnostics. You can point your finger at me, and I'll just ask you to open a pull request to make things better, because there's a lot of things in LDF that can be done better, and I just don't have enough time to do it. And then I'm also really excited because with Cupid, we're able to run ILAM. And so Keith and increasingly Sam have been the two gateways to run ILAM. And with Cupid, it makes running ILAM a whole lot easier. So that's exciting. Yeah, so I think post-processing is getting more streamlined. Probably not fast enough, but it's doing better. The other thing I'll note here is that it has zero capabilities to handle anything faith related, and so I think an urgent call for the community will be to what's that?
Not zero.
Not zero. Well, it's not out of the box.
Change the variables.
Right. You can compare a fates case to a fates case pretty easily, but comparing a fates case to a big leaf case will cause some problems. So the capabilities are there, but all the options aren't as out of the box as I'd like. CSM, I'm calling this CSM3X. I'm not exactly sure when. I think the proposal says CSM31 will have water isotopes enabled. So this is a project that's being led by Sylvia D out of Rice and Zhang Zhu, who's a scientist here in the paleo group. So we'll have water isotopes enabled in an upcoming version of CESM3, which is exciting. It's going to be in Mizraut, so kind of helping to pivot the community to using Mizraut as the default river model. And on land, those are the kind of two pieces that are most relevant to the working group, but it's going to be throughout the CSM system. So this is supposed to be a way to really enhance our science by having water tracers enabled in the model. If this gets you really, really excited, I'd encourage you to get your phones out and take this survey. We're really looking for input for the community for how you think you might want to use this. And John asked for folks to kind of provide their feedback about applications and features that you want to make sure that we have enabled in the model. So Bill Sachs is doing a lot of this on the land side, and Naoki's handling this for Mizraut. Right, I'm going away. I want to talk a little bit about how the land model working group and biogeochemistry working groups provide links to CESM. And this is a very simplified representation of how, we already heard today how biogeochemistry feeds back on climate, and climate feeds back on chemistry, and then the chemistry feeds back on the climate. And chemistry here, I'm meaning is atmospheric chemistry. So it's kind of this chicken or an egg problem. And that's mostly acute for initialization. So hopefully soon we're going to start the arduous process of actually spinning up CESM3. I think the plan is to run, kind of 2 iterations of this climate chemistry feedback where you run the model with kind of simplified atmospheric chemistry for 100 years to generate, a kind of stable-ish climate to get to run the more expensive atmospheric chemistry model that provides forcings that go back into the climate model. So we'll do a few of those to generate eventually coupler history output to spin up CLM and the ocean and the BGC and the ocean model. So it'll take, I don't know, a month probably to do these kind of iterative climate chemistry feedbacks. And then the biogeochemistry in the ocean is going to take a couple months to spin up, most likely. So you can ask Dave now at lunch, whenever you want, when we're going to start this. I think all of us are really, really, really anxious to have started this months ago, and we're hopefully getting close to that stage. We're still looking for that stable climate before we can really start this process. I don't know if this is still true. We're hoping by the working group meeting that we've got a PI control for the CESM workshop, that there's a CESM3 PI control that'll sort of be like the starting point for CESM3. I think, so that's kind of the update that I have. Again, trying to focus on the positives and the future for the working group, and still kind of, I guess, acknowledging the rocky road in the short term that we have. But I'll stop there and open it up for questions and comments.
Plenty of time for questions.
A little bit of time, yeah.
Just something that came up at the end of the ESP working group meeting, and I don't know if other folks were there, was the role of land initialization. And it came up a little in Kyle's talk too. So I'm just wondering what the working group is thinking along those lines and whether we should have more interaction with folks from ESP and.
Yeah, we should.
Yeah.
Do you have ideas about how to facilitate that or what the bridge is?
Yeah, I don't know. I think that it's something that keeps coming up and that people don't seem to fully understand the best way to initialize land for hindcasts and forecasts. And so I don't know, maybe we can pull.
I guess I'm curious, like, was there a clear direction from their submission with you about like what their next experiments were going to be or?
Yeah, I guess we'd have to maybe talk to Steve about that. Like, I think there is a plan for kind of next generation hindcast and forecast beyond like the CSM2, S2S, and SMILE. So either with CSM3 or with, so I'm not sure, but I think that question is going to come up again.
Yeah, because in high res applications too, people are always wanting to know how to initialize the land model. I'd say we're lacking in expertise maybe, and the best ways to do that. And so we tend, at least I'm guilty of just like doing the way we always do it. And maybe we need to come up with better ways. I'm really intrigued by Kyle's idea of just running for a year, like that, hoping that's enough to get a snowpack that's realistic. In some ways that has some appeal. It's like, oh, that's a short spin up. You can't do that for hard type of questions, obviously. Yeah.
Yeah, so thank you for all the update. So when you talk about like the ILAM, those all the diagnosis package, I guess we have to keep in mind that there are huge uncertainty for the benchmark data. For example, the GPP you use as example. We don't even know whether 125 is a good target. Yeah. So, and also LAI. So you mentioned like tropics as example. But if we look at the MODIS LAI data set, this shows like huge seasonal changes of LAI, which is basically wrong. That's just because of clouds. But when we look at the different data sets, the pattern is totally different. So I think when we look at the benchmark data and look at those statistics for the different metrics, the uncertainty of the data as benchmark is also very important.
Yeah. That's something you're pretty stuff a lot more about.
Yeah, we're going to talk about parameter ensembles and trying to sample across that observational uncertainty and get an estimate of parametric uncertainty tomorrow. But I think we're well within the observational uncertainty with that GPP of 130-ish. So I'm pretty comfortable that we're within the observational tolerance. Yeah, that's probably what you calibrate to.
I mostly just wanted to when we go make this island bigger and add our new latest runs, it's going to look like a degradation. But I think at least Lydia and I are aware of that, and we just I wanted to make everyone else aware of it. Like, hey, we made things worse.
Yeah, trying to split the difference between BK's, the coupled model looking good and the offline model looking good.
Yeah, you're pointing out, and I didn't try there's 4 LAI products and 3 GPP products or something that are in Ireland. So some of that observational uncertainty is under the hood, but you don't see it on these stoplight diagrams that Ireland makes. But you can dig in and learn a lot more. My interest is just to make these tools easier to use.
Katie's got a good point, right? This is a perpetual problem. We do need to find a way to address this. I don't know how we do it, but with knowledge, I think it's pretty important because I think we're going to be doing initialized prediction more, right? That's almost certainly that's going to be a bigger part of the portfolio of work that we're going to be doing here at NCAR and the community is going to be doing. And we'd also like to use it for trying to tune the model and things like that. So, but we're all aware of this. I agree. We don't have the expertise. That's what we need to keep that.
Well, I think we could probably develop the expertise. I'd say it's more a person power problem.
Yeah, person power attention to it.
Yeah.
But I wanted to actually just raise. I don't think it's going to get raised anywhere here, but I think a couple of exciting data sets that either exist or going to exist. And I don't know if Peter's giving a talk, but there's pretty big data set now on emissions-driven fire, interactive fire. We've heard about it before, climate intervention, and a lot of CDR, like different methods of seed here. So that's a cool new data set that has a lot of things we can be using it for. And the other is this thing WEMIP that we're going to participate in, warming induced emissions. And MIP, and the reason that's interesting is it's like the extension of Trendy into the future, but also we're going to try to use the hill slope model potentially. And so exploiting, pushing in to the per time to actually be using the hill slope model for production level transient climate runs. So maybe just it's coming down the pipe, hopefully.
Yeah. So WEMIP is a warming induced model air comparison project that Spark is funding, which is a foundation interested in doing funding good science, which is pretty cool to actually get funded to do it. So Sean and Peter and I are sort of spearheading that. And it's basically trending through 2300. It's kind of the short with the levels of greenhouse gas emissions. Other comments, questions?
Can I just make a comment? Like, I think there are all kinds of super interesting science questions that are unexplored in the interaction with atmospheric chemistry and land processes, because there hasn't really been a model in which all of those things could be manipulated at the same time. And so, the atmospheric chemistry community is really big on geochem, but geochem just runs on atmospheric reanalysis. Right. And so CESM in some ways offers a unique opportunity to explore some of those interactions, which I think there's all kinds of good questions that are unanswered just because a tool didn't exist to answer them.
Yes. Yeah. Yeah. And I think, where I end up seeing that is mostly on the nitrogen trace gas fluxes. There's active community with very well working and companies that are doing that kind of work. And it's always hard because it feeds back at they tinker around with trace gases, but then it feeds back on the carbon cycle.
Well, we
don't want it.
Or you get a totally different oxidative capacity atmosphere. So feedback on everything.
Right, yeah, it feeds upstream too, yeah. It introduces some really interesting calibration pickups, but especially at this stage where we don't have the calibrate model, we want to do science. That sounds like fun. Cool. Are we good?
Yep. Head down to lunch. You can follow the flow to the cafeteria. I'll be back here at 1:15.
Okay, well, I think we're going to get started again. So our next set of talks is going to be focused on, looks like soil moisture and drought and land surface processes. So our first speaker is going to be Jerry Meal. If you want to come up, get your mic. Yeah. Okay, great.
Interesting connection to initialized soil moisture anomalies.
Excuse me, Jerry.
Yeah.
Can you turn on your microphone?
And Adriana, you close it.
Thank you so much.
I'll take a look at that.
All right. Okay. So I was saying, I kind of stumbled into this because there was a paper that was published 2 years ago by Peng Pei-Shi and Ruby Lung and other co-authors, and they claimed 2-year skill in predicting the 2003 European heat wave by initializing soil moisture over the Tibetan Plateau. So well, that's kind of interesting. How can that work? So we said, well, let's look at it in our initialized hindcasts with SMILE experiments we've done, the seasonal multi-year large ensemble with CSM initially. We're going to look at E3SM as well, see if we can see it. Well, we didn't see much of a connection to the Tibetan Plateau 2 years in advance, but we did see a connection to the U.S. 1 year in advance, to soil moisture anomalies over the U.S. 1 year advance and in 1 year in advance. So how could that possibly work? And so we think that the mechanism for how you could connect land surface conditions over the US to what's going on in Europe in terms of heat extremes and drought is through this kind of mysterious wave 5 teleconnection pattern. And Haiyan Teng and Brandstetter and others looked at this in a number of different contexts. That's just one of their papers, and this is a figure from one of their papers. And they were looking at the Dust Bowl drought, and they were trying to figure out if the Dust Bowl drought in the 30s over the U.S., of course, the whole central part of the U.S. was dried up because of disastrous land use practices, basically plowed up all the grasslands, and then there was a naturally occurring drought, soil dried out, and then the heat just went up, and then dust started, and that made everything worse. And so you had this kind of convergence of really nasty factors that contributed to that really unusual event. But it seemed to have this connection to other parts of the Northern Hemisphere, and the mechanism for this, they were hypothesizing, was if you put this lower tropospheric heating in other words, the surface gets really hot, so you're heating up the lower part of the atmosphere. If you put that in a specified heating anomaly experiment, just with the atmosphere only, you see this wave 5 pattern going around the Northern Hemisphere. This is in the summer, so this is kind of an interesting twist on the usual. We're looking at teleconnection patterns in the winter coming out of the deep tropics, like the PNA pattern, big Rossby wave kind of things. But this is a summertime wave 5 teleconnection pattern. You can see over the U.S., the heating profiles on the right there. That red line shows how warm the lower troposphere was when she put this conditions in. And these H's indicate upper level highs, or heat domes, you could call them, going around the Northern Hemisphere. And there's one over the US, and then one kind of bridging parts of Europe there, going over to Asia and over the North Pacific. So maybe there is a way that what's happening over the US in terms of land conditions could affect what's happening over Europe. So we followed this up to see if we could see any effects of this Dust Bowl drought in other parts of the Northern Hemisphere, if this wave 5 pattern was actually working. And so we came up with this extremes index. It's the ratio of daily record high maxima to daily record low minima. And so if you expect that any station has an equal chance of setting record high or record low on a given day, this ratio averaged over some period of time would be about 1. But if you start skewing the odds towards record heat or record cold, this is going to deviate from 1. And in fact, the records ratio over the 30s there in the upper left panel was 2.5. In other words, there was
the visitor networks.
in the upper right panel, you see there this records ratio over Sweden, and in the 30s, the records ratio is almost 3. There was no Dust Bowl drought over Sweden in the 30s. If you look over Germany, this ratio in the 30s was about 1.6, so it's well over 1, and it stands out, and you didn't see bigger records ratios until the 90s and 2000s over Germany. Over Russia, it was about 1.5 in the 30s, and didn't exceed those until the 80s or 90s. So it looked like there was a connection to these heat extremes to what was going on over North America. And the hypothesis we had in our 2022 paper was that this was this wave 5 teleconnection pattern. So this is on the decadal timescale, right? So the question is, could this actually happen on interannual timescales? So could we get predictability out of initialized soil moisture conditions over the US, what's happening downstream on decadal timescales? So as a case study, and motivated again by this Xie et al. Paper, let's look at this 2003 European heat and drought as a case study. So what was happening, and this would be the initial state in the US, in 2002, there was a pretty severe drought, and it was pretty hot. So the initial state over the US would have been heat and drought. And of course, when you look at what was happening in 2003, that those drought conditions kind of persisted over the US. And 2003 was when there was the big European heat wave, resulted in many deaths. And of course, the drought was made worse by the heat. So to look at this connection, we're going to look at this as a case study. We're going to look at hindcasts initialized in May 2002 for the prediction period, June, July, August 2003, so a 13-month lead over a year in advance. And we're going to look at the SMILE hindcast with CSM2. These are going to be initialized in May 2002 and analyzed for the 13-month lead. These are 20 ensemble members of these hindcasts. Our ocean initialization is the so-called forced ocean sea ice, or FOSSI. This is kind of the standard way we've been initializing our hindcasts all along at NCAR. Soil moisture initialization is a little bit different. What we did is we took the CLM from CSM and ran it offline with observed atmospheric forcing. Basically what we do is to initialize the ocean, but we're doing it with the land model. And this is this trendy CRU GRAV2 data. And the soil moisture in the hindcast is initialized with these land initial conditions from this offline run with the CLM. We're going to be comparing this to some observed soil moisture. And of course, observed soil moisture, as you all know, is always kind of dicey. This is a satellite-derived product. There are a couple other things out there, reanalyses, but we were going to try this first just to see what we got. HADIS for observed SSTs and ERA5 for observed atmospheric fields. Okay, so this is our initial soil moisture anomalies for May 2002. So this is the initial state where we're putting in as our starting point for this prediction. The circled area, the red colors are dry soils, and you can see over the U.S., western U.S., you see those red colors, it was anomalously dry. That's the initial state. You can see in the right there, the drought monitor was showing drought during that time period, and these observations from this satellite-derived product also show dry conditions, those red colors over the western U.S. In May 2002. But in both the model and the observations, if you look over Europe, there's really nothing going on. So there's a big anomaly over the US, but not much over Europe. And that's our initial state. And then we run the model 13-month lead and look at soil moisture anomalies. And as we saw in the observations there on the right, and also we're going to look at a second, the observed products there, the dry conditions persisted into June, July, August 2003 over the US. But now you see this big change in soil moisture over Europe. And you see those red colors over Europe, indicating that dry conditions have really set up over Europe in this prediction, which is kind of interesting. What was happening in terms of surface temperature, as you'd imagine, the predicted surface temperature anomalies for June, July, August 2003 in the upper left from the model hindcasts, red colors over the western US indicate anomalous warmth. And as you'd hope for, in this case, you see anomalous warmth, the red colors over Europe at 13-month leads. Compared to the observations, you also see warm western US and of course really hot over Europe, as you'd expect. As we saw before, the predicted soil moisture anomalies show these dry conditions over the western US and also over Europe in 2003. The observed soil moisture anomalies for the summer of 2003 also show dry conditions over the western US and of course dry conditions over Europe. So it looks like we're getting some kind of predictive skill somehow from these initialized land surface conditions that we had a year in advance. If you zoom in to see regionally how we're doing, of course, then it gets a little bit less pleasing. But on the right there, the observations, the heat in Europe was mainly over France and Germany and some of the other Western European countries, Northern Italy. In the model, we're getting most of the heat over Spain and Southern France. Excuse me. And you can see the magnitude of these anomalies are about a third in the model of what they are in the observations. But I was just amazed we got anything that looked anything like the observations. I mean, this is a one-year prediction, right? And so to me, that's pretty interesting. Okay, with the mechanism, what's doing this? So we're back to this wave 5 thing, right? So if you look at the predicted 200 hectopascal height anomalies for June, July, August 2003, initialized the year before, you see over the western US an upper level high, and you see a series of 5 upper level highs going across with one right over Europe. And so that's this wave 5 connection between heat over the US and heat over Europe, because you get this big upper level high, big subsidence, everything dries out and heats up at the surface. The observations also show a very similar wave 5 pattern. See the big high over the western US there, big high over Europe, and also this wave 5 pattern. So it looks like this is probably the mechanism that's connecting what's going on over the US to Europe in terms of this 2003 heat wave. And again, our idea here is that this wave 5 connection, again, this is an idealized experiment, which is not going to be exactly what we see in the observations, but the idea is you get conditions over the central part of the US or central or west part of the US that can convey upper level highs over parts of Europe and then also into Eastern Asia as well. We didn't touch on in this paper, there's also some interesting things going on there. Okay, so previous work demonstrated these very dry soils and associated heat extremes during the Dust Bowl in the 30s can be connected by this circumglobal wave 5 summer teleconnection pattern to heat extremes in Europe on decadal timescales. And then we asked the question is, could these connections actually work on interannual timescales to give us some predictive value from what's going on over the US to connecting what's going on over Europe? So we looked at initialized hindcast case study to try to predict the 2003 European heat and drought. So the initialized negative soil moisture anomalies in the Western US in May 2002 are comparable. That was another surprise because we didn't really know how well this kind of initialized soil moisture we were doing, this offline CLM running observed to atmospheric portion. We didn't know really how that was doing. And it's doing actually fairly well. They're comparable to the observed soil moisture anomalies in May 2002, but there was nothing really going on over Europe in May 2002. But then when you look at the prediction a year later, you see that the summer dryness persisted and was also predicted in the model over the US. But then you also got this connection through this wave 5 teleconnection pattern, this anomalous high over Europe and this anomalous heat and drought over Europe in June, July, August 2003. So just as addendum to this, because I gave this talk at the ESPWG, I guess a couple weeks ago, and Ruby Lung was actually on the Zoom call, and we were kind of trying to figure out live what was going on between her results and our results. And we thought there's kind of a chain reaction. So maybe what's happening over the Tibetan Plateau in 2001, those dry conditions, and it was really dry over the Tibetan Plateau then, maybe that then connects through the wave 5 pattern to the US a year later. That dried out the US, or at least contributed to it, which then connected to Europe a year after that. So Sasha and I are just looking at some plots right now to see if that could be something that's going. Moisture may be able to give us some predictive skill on interannual timescales for some regions under certain conditions. Thanks.
Great. We have time for a couple questions. Yeah.
Jerry, for the Ruby study, did you only look at soil moisture? Did they also consider snowpack over the Tibetan Plateau?
Well, in retrospect, she was thinking that maybe the snowpack was more important than the plateau. And we haven't looked at snowpack yet. We were just looking at kind of soil moisture and surface temperature. It looks like there could be some connection to North America, like from 2001 to 2002. We just started looking at those results, but of course, there's a long history of snow cover over the plateau affecting all kinds of different things. Southeast monsoon in particular, going back to Blandford in the 1890s, but even more recently, there's a whole project now in GWAX looking at initialized soil moisture over the plateau and how that could contribute to S2S predictability, so subseasonal to seasonal. So there's a lot of interest in this kind of thing, and it looks like for us, it looks like maybe there's a couple sweet spots in the Northern Hemisphere that you can tweak this wave 5 pattern. Tibetan Plateau could be one, because I also looked at Tibetan Plateau and got the same wave 5 pattern, and maybe the US. And the speculation is, John Sulo speculated, maybe that's because those two areas are just upstream with big jet exit regions going off into the North Pacific and North Atlantic, and maybe that somehow you can tweak the eddy fields and get these things to teleconnect in this particular pattern. And why wave 5? It seems to be something with the geography of the Northern Hemisphere, how these things set up in terms of land and ocean contrast.
Thanks. Okay. I think we have one question as we're setting up for the next speaker.
Yeah. It's really nice to hear that the land is doing something. So thank you. And I'm curious just how to square this idea that there is some predictability from soil moisture states compared to what Yaga's showed, that it seems like the land offers no predictability.
Well, she was looking at all predictability for every initial state, right? We're looking at one particular initial state where we kind of selected it based on the expectation that we may be able to see something for those conditions and that particular setup. So you may be situation dependent. There may be tremendous opportunity, which you hear a lot about in the predictability community, where there are sometimes you may be able to get predictability, other times you won't in conditions. But I think and the way the S2S initialization for soil moisture is a little bit different from the SMILE multi-year. That probably doesn't make a big difference, but that's another thing that's a little bit different. But yeah, it's intriguing to think about exactly under what conditions you get this predictability. Yeah.
Hey, Jemai.
All right. So yeah. So next we're going to from Nazanin Tavakoli. Sorry if I butchered your name. But about diagnosing biases in soil moisture evaporation coupling metrics.
You gave us the advice on which soil moisture data set.
Good afternoon. Good afternoon, everyone. My name is Nazanin Tavakoli, and I am a PhD student working with Dr. Paul Diermeyer. And today I will present one of my current research, diagnosing biases in soil moisture evaporation coupling metrics in air system models using covariance discriminant analysis. So let's start with basic of land-atmosphere interactions. So land-atmosphere interactions involve a series of feedback mechanisms within the air system. And the land surface states serve as the initial element in this feedback mechanism, and soil moisture is among its most influential components, since it plays a critical role in shaping the weather and climate conditions. By partitioning available surface energy between latent flux and sensible heat flux, which in return affect near surface atmospheric conditions, boundary layer properties, and ultimately the formation of cloud and precipitation. So there are lots of coupling metrics that combine statistical techniques with physical processes, and many studies have been made to quantify these metrics using observational data sets, reanalysis products, or air system models. However, there are still large discrepancies in these coupling strengths and type across air system models, between model and observations, also reanalysis product and observational data. Also, they disagree in capturing these interactions. Therefore, Tavakoli and Diermeyer, we develop a global data sets of LA coupling metrics based on observations while accounting for the random observational errors in the soil moisture satellite time series using the Markovian framework. So here you can see the observational adjusted metrics, two of them, adjusted Pearson correlation and adjusted terrestrial coupling index. These two are two of the metrics that we produced. So now consider that we compute correlation between soil moisture and evaporation from model outputs. And we have another map from observational correlations. So we can compare these two correlation. We can do some significance tests to see, for example, where the model correlation is significantly different from the observations. But the point here is that using correlation, because correlation is a normalized measure, somehow we are throwing away this magnitude of variability. So then we can compute the variance of the soil moisture from the model and compare it to the variance of the observed soil moisture. But in this case, somehow we are comparing soil moisture independent from these quantities. And because soil moisture evaporation coupling, they are inherently joined with these quantities. So because these soil moisture and evaporation coupling form a system, from a coupled system. Therefore, in this study, I am using covariance discriminant analysis, CDA, to identify the linear combination of soil moisture and surface fluxes where the greatest separation occur between two distributions. Or in other words, this study highlights the direction in which the model variance structure differs most from the observations. And then we can see where is the model soil moisture surface fluxes coupling structure significantly different from the observations, or is there any systematic seasonal pattern in this structure? And most importantly, we can answer this question. If there is a disagreement between model and observations, this disagreement is dominated by variance of the soil moisture, variance of the surface fluxes, or their covariances, and how much are their contributions. So why it matters, because hopefully these results can guide the model development, especially it can improve the parameterizations in the models. So in this study, I am using CCI as an observational soil moisture. And also, I am using observational based gleam product for the surface heat fluxes. And for the modeling part, I am using CLM5. And in this presentation, I will only show you the results between soil moisture and evaporation for 4 seasons. And all of the analyses were conducted at a spatial resolution of the model. So let's start with this question, how we can compute CDA eigenvalues. So at first, I extracted covariance matrices for both model and observations. Then I took the differences between these two matrices. And then I solved the generalized eigenvalue problem by these equations. Here we have the differences between the covariance matrices. We have eigenvector and eigenvalues, which can tell us how much disagreement is between the covariance of the model and observations. So by having eigenvector, we can define a linear combinations for a specific mode, for example, for the first mode. And then in the next step, we can calculate the contribution of differences, for example, in the soil moisture variance to the total variance disagreement along a specific mode. So then we can take the absolute value of this contribution and normalize them to answer this question: how much of the total CDA variance disagreement along a specific mode is due to the model observation differences in their variance of the soil moisture, variance of the evaporation, or their covariance. And for the significance test, I use permutation test to assess whether the observed eigenvalues could arise by chance if the model and observational samples are coming from the same distribution. Or in other words, the null hypothesis here is that the covariance matrices of model and observations are not distinguishable, so we can exchange samples. So at first step, I formed pairs of soil moisture and evaporation from model and observations. Then I randomly permuted the time indices of model and observation pairs separately and pulled all of the shuffled pairs together. And I randomly split them into the two groups of equal sizes. For example, the first group is synthetic observation, the second one is synthetic model. And I redid all of the calculations, computing the covariance matrices and their differences, and I extracted the first two eigenvalues for this permutation. And I repeated all of this iteration for 1,000 times to obtain the empirical null distribution for the first and second eigenvalues, and also to calculate the p-value. So let's move on to the results section and see where and how strongly the CLM model deviates from the observation in the first and second mode during the JJA. So these gray areas are showing the areas that the eigenvalue is not significant, and the white are showing the areas that we have missing values, mostly in CCI. So the absolute value of these eigenvalues tells us how big the relative variance disagreement is between the model and observations. And the sign can tell us whether the model variance is too small or too large compared to the observation variance along a specific mode. For example, if the eigenvalue is near the zero, means that the model variance along that mode is very close to the observed. But when we have a positive values, for example, mostly over the drier regions like India, some part of the Middle East, or western part of US. So it means that the model variance along that soil moisture evaporation mode is smaller than the observed variance, or in other words, CLM is underestimating the variance. But when we have negative values like most over the wetter regions, high latitudes, or eastern part of US, we can say that somehow CLM is overestimating the variance. But this pattern is not fixed, so maybe we cannot say that drier regions over the globe, they have positive, or wetter regions, they have negative. Maybe we can say that over the arid or semi-arid, we have positive values. But for the second eigen values, we can see a mixed pattern of positive and negative, but we can see that over most part of the globe, we have positive values, means that the model is, CLM is underestimating the variance. So that we have seen the JJA solids focus on the other seasons. Based on this figure, we can see that definitely there is this seasonal pattern for the first and second eigenvalues. But there's a question that right now I don't have an answer for that. Why, for example, in some locations for the first eigenvalue, we have negative values, and for the second one, they have sign of positive. They are showing as a red here. So in the next step, I calculated the variance explained by each mode, and this figure is showing the variance explained by the first mode in blue and the second mode in orange. And we can see over the 4 seasons, and we can see that although the most of the variance is explained by the first mode, around 30-40% of the variance is explained by second mode. So, which is not negligible, and this means that there is some information in the second mode that should be explored in the future. And finally, this figure is showing the fraction of disagreement attributable to the soil moisture variance, and these colors are showing the fraction. So what we can see here is that contribution coming from the soil moisture variance is high over the high latitudes or wetter regions like eastern part of US. So here we have an assumption that maybe CLM struggles with some hydrology problems, maybe precipitation, which is the most important terms in the soil moisture. But this is the hypothesis. We are not sure about this right now. And this column is showing the fraction of disagreement attributable to the variance of the evaporation for the first mode. And we can see that most over the arid regions like Australia, western part of US, some part of Sahara, and the contribution coming from the variance of the evaporation is highest. And also here we have another assumption that maybe there is a parameterization issue with the CLM in the evaporation and transpiration. And finally, this column is showing the fraction of disagreement attributable to the covariance differences. So although the magnitude of this contribution is less compared to the first two, but it has a very interesting pattern that we can see that the contribution is highest over the transitional regions like India, like Sahel, and also this column that we are in the DJF means that we have a summer in the south hemisphere. These locations are all known as a transitional or monsoon areas. So this means that this contribution is highest over the location that we have a dynamic situation. So in this study, we applied covariance discriminant analysis on the covariance matrices of observation and evaporation to identify the direction and magnitude where the CLM model differs most from the observations. And here is the summary of this work. And In the future, I will apply this approach to other variables and CSM and MPAS no MP. So this study is very new and all of the results are preliminary. So any feedback and comments are welcome. Thank you.
Thank you so much. So unfortunately, I don't think we have time for questions, but please ask Nazanin during the discussion or later. I think that was a really cool talk. Okay, so next we're gonna hear from Ben Puchavecki about evaluating drivers of evapotranspiration. Here you go.
Awesome, thanks. Yeah, so today I'm going to talk about how we're finding some distinct patterns of ET across a couple of perturbed parameter ensemble. And I'd just like to thank everyone who's been really helpful getting the simulation running and collaborating with to get this PPE actually completed, which has taken a bit. So, you know, ET plays a crucial role in land hydroclimate. Probably don't need to reiterate this to this crowd, but ET depends on physical and biological processes across many scales, from the surface energy balance, depends on large-scale hydrology and vegetation, as well as stomatal processes that affect the transpiration. And we know that climate and ET have kind of these feedbacks where climate or ET is a function of both biology and climate, and such climate variables, things like clouds, temperature, and precipitation can impact ET. But we also know that ET is this flux of energy, water, and carbon from the land to the atmosphere. And so there are feedbacks there. And I just want to briefly show this plot from Claire Zarakis showing actually quantifying how where and kind of the magnitude of these land atmosphere feedbacks on changes in ET. As you can see in these blue regions, the feedbacks are actually dampening changes in ET. And the red regions these feedbacks are amplifying changes in ET. And this is all important because ET is really crucial for climate projections. It's important for water availability, drought, heat waves, and precipitation. However, it's pretty difficult to untangle individual controls of ET, and this is likely mostly because of just challenges to quantifying ET globally. There are few in situ measurements, and then remote sensing kind of products depend on assumptions and some implicit modeling there. And because of this, there have been a lot of contradictory explanations for historical ET trends, kind of drawing on different drivers, including vegetation greening, soil moisture, stomatal closure, and other kind of elements of the Earth system. But crucially, kind of moving forward, we're really interested in what will dictate ET under future climate. And so we're going to look through kind of at this historical period in a series of simulations to try to kind of determine some processes that are affecting ET and how they're affecting ET so that we can project that into the future. And to do this, we're going to use a historical coupled PPE. And so CLM represents the processes that we believe are important to determining ET. And so we're going to go into the model and we're going to perturb the CLM parameters across some functional space, as you can imagine in this little schematic, where different parameters affect different functions or kind of processes within CLM. And then we used actually land-only PPEs to select these parameters, determining kind of which axes to sample in this functional space, as well as just picking parameters that generate large changes in ET, because that's what we were interested in. And then we're running the PPE under historical forcing with observed SSTs and to generate many realizations of climate and ET over this historical period. And so just to briefly kind of summarize the configuration here, again, we're using a couple of land atmosphere configuration, and we're prescribing time varying SSTs. And then we have 14 parameters in CLM that we picked, and we're perturbing them one at a time to a high and low perturbation based on their uncertainty range. And then we're starting from equilibrated land initial conditions in 1950 and running until 2015. And I think, so one thing I didn't note here is that it's a 2-degree spatial resolution. So I just want to start off with kind of looking at the global mean ET. And so here are just ET observational products I grabbed from ILAN. And so you can see there's a fairly large spread in just the observational products mean state globally. And here is the Linea's CLM6 transient PPE, which actually we used to select some of these parameters. And so this is kind of our prior expectation of where our PP that we're running under coupled simulation or coupled configuration might lie. And then here's our FHIST or coupled PPE that we ran. So again, kind of similar, like range here. Maybe the mean and median are shifted a bit higher, but similar spread to the offline PPE. And honestly, like the spread is almost comparable to that of just observational products in the mean as well. And then for context, here's the large ensemble. And so we're getting much greater spread in the PPE than the large ensemble. However, when you look at the anomaly, so you're subtracting out the mean from each ensemble member, you see that these lines kind of collapse. And so the gray lines are observational products, and the blue line is the ensemble mean with one standard deviation, and then the extrema. So again, it kind of collapses along that, along the observations. And similarly, like we get a similar spread when you do this when you look in this anomaly space for the large ensemble as well. So primarily, these perturbations are changing mean state ET as opposed to changing like the variability once you remove that mean. And then I did some very preliminary trend analysis, and this is in the global mean. There doesn't seem to be a big significant difference in the global mean ET trends across our PP relative to the large ensemble. But there are some differences in the regional trends, which I haven't focused on in this talk. And then briefly, part of the reason why we get large changes in ET is because of large changes in LAI. And so this is again, the PPE and some observational products. And for context, this is where lens sits. So we're getting really significant spread in LAI across this coupled PPE. But we're interested in kind of where and how these parameter perturbations change ET. So here I've grabbed this one parameter Kmax, which changes plant segment conductance. And so the minimum perturbation you can see has pretty strong decreases in ET in most areas of the globe, where the max perturbation has pretty strong increases in ET over the tropics, in the tropical rainforests. And then just to note, like from now on, I'm going to be focusing on the time mean from 1995 to 2014. And the delta is just the perturbed experiment minus the default experiment. So we're quantifying the effect of the parameter perturbation. So initial takeaways, I think, as kind of expected, these responses are very nonlinear to like the high and low perturbation. Kmax min versus Kmax max, the spatial pattern and magnitudes are fairly different. And not shown here, we also see very strong compensation of ET components, which I'm happy to talk about offline. But kind of the tricky part here is that it's difficult to just look at these maps and see how things are different. So we're going to define it. We're going to transform latitude and longitude to this LAI aridity space. And kind of this is based on our prior expectation that ET is going to behave differently depending on the mean state, LAI, and aridity. And to briefly walk through how we did this, we take LAI, we compute, we take the 2D data set, we collapse it into a single vector, compute these quantile bins, and then can kind of basically remap that onto Latin lawn space to create these bins where like the low bin is low LAI and the high bin is high LAI. And we did the same for aridity index, which is actually pretty nice because it's a very nonlinear index. And so you can actually create kind of a smoother map here with these quantile bins. And again, on the kind of a lower quantile bin, it would be a wetter, less arid region, where a higher quantile would be drier, more arid region. And then we're plotting these on, and this is how the plots are going to be for the next part of the talk, in this LAI aridity space. So in the upper left, you have high LAI and low aridity, whereas in the lower right, you have low LAI and high aridity. And then once we bin all these grid points, you can compute the mean change in ET in these quantile bins. And so again, this is a return to Kmax min, where we can see that in this kind of LAI aridity space, we have pretty strong decreases in ET across this space. But you might notice, again, some like positive or increases in ET, which are probably right in the southwestern United States and maybe bits of South America. And we did this for all the ensemble members. And I just wanted to kind of grab a couple and show you how these patterns are quite different across the ensemble. And so this is, again, Kmax min, and then a return to Kmax max, where, again, most of the, it's a strong increases in ET in these tropical rainforests. So it's high LAI across kind of the entire aridity gradient. Also for context, these little circles here are actually the number of grid cells in each bin. So some of the ones to this kind of upper right-hand side of these plots have pretty few grid cells, so not as important. And then here's FFF, which controls, it's a parameter related to soil hydrology. And so here in the minimum perturbation, again, we see that there are strong decreases in ET, basically kind of across LAI quantiles, but mostly in arid regions. Whereas the maximum perturbation has a kind of fairly, maybe, somewhat uniform increases in ET, but the increases are greater in higher LAI, more arid regions. And then here are some other parameters as well, just to kind of illustrate that we're seeing kind of very different patterns across the parameters, which is pretty interesting and I think provides like a good starting point for future analysis. And I think, it's just pretty interesting to see that there are different patterns here and from different functional, different parameters that are controlling different processes or creating, affecting ET in different LAI aridity bins. So just kind of some key takeaways. So we performed a coupled historical PPE with prescribed SSTs. We find there's pretty large spread in the mean land climate state, but not as much difference in global mean trends. Again, I did start some like grid cell like trend analysis, and there did seem to be some regions that popped out. But at least in the global mean, it's not that different across the ensemble. And then we also kind of showed that transforming into this LAI aridity space kind of reveals some distinct patterns of parameter-driven ET change, which suggests, again, diverse mechanisms. And from what I've listed into to some of the like CLM meetings, maybe could be useful for model tuning. I'm not sure. And then moving forward, I think one of the things in looking at some of these bin plots, we did notice that there are some differences seasonally. And so I think looking at arid versus humid months or just kind of plotting these type of bin plots across the seasons would be interesting. And I think we will start to see some differences or similarities between the ensemble members. And then kind of more broadly, I think these patterns it'd be interesting to see if future projections capture similar modes of ET variability in this space. Like, are these parameters kind of sampling a wide range of things, whereas the future projections, when you increase CO2 and warming, are only really changing ET in these kind of certain spaces in this LAI aridity plots. And then also doing a bit more robust trend analysis, I think would be interesting. But overall, it's a pretty rich data set, and I'm pretty excited to kind of look at it in more depth. So yeah, thanks.
Thank you. Well, you have time for like one question? Katie.
Thanks, Ben. I really like your LAI visualization plots. Have you thought about how you could get them to look at the space between the min and the max parameter values, so that the distributions of the parameters in the cell, like not just like what happens when you make the map of perturbation and the bin perturbation, but like what's going on in that space, and that could relate to the usefulness for model tuning.
Yeah, I feel like that's a bit tricky just because we don't actually have simulations that sample that, in between space. So at the moment, I don't know how to do that.
Okay, thank you. Okay. Okay, next we're gonna hear from Evan Martella. Okay, Evan is going to talk about functional diversity.
Thanks, Adriana. Hi, everybody. I'm Evan Margiotta. I'm a grad student at UCSB. And I'm really excited today to be continuing to talk about our work looking at the role of functional diversity in land surface modeling and in CLM, trying to answer where, when, and maybe even why it matters for the terrestrial carbon cycle. So to start with just a little bit of simple background about the importance of plant diversity in buffering ecosystems to disturbances. There's a nice little figure from Cleveland in 2011 showing an idealized ecosystem made up of two species, blue cold adapted species and a green warm adapted species. And we see in communities that are formed of just dominated by a single one of these species, there are inevitably going to be years where the climate is unfavorable to their competitive advantage, and we might see mortality and a disruption of ecosystem services. However, in communities where there's a mix of kind of resource acquisition strategies and stress adaptations, we're going to see kind of less of these disruptions because organisms are going to be able to take advantage of their competitive advantage during years where their competitors might die off. And that's going to allow them to stabilize ecosystem functions and allows us to think that these diversity stability effects may be an important mechanism regulating carbon fluxes during disturbances. So maybe not seeing as strong flux anomalies during droughts in areas with kind of more functional diversity. But kind of in a land surface modeling world, we're often making a lot of assumptions about the kinds of competitions we can model or about the limits to vegetation heterogeneity we can represent in a kind of a PFT framework. So some folks have been thinking about this over the last decade. I've pulled a couple like key figures from some studies that have looked at this. The first one using the LPJ model at a single site in the tropical forest, running it in a high diversity and low diversity mode, basically just increasing the number of PFTs to better fully sample across the functional trait space. And they find that when they increase the diversity, that we see stronger biomass recovery after kind of climate-based mortality. And then kind of a similar approach using ELM across 15 different flux tower sites, didn't find a consistent effect of increasing the number of PFDs and increasing the functional diversity in terms of gross primary productivity. It didn't necessarily improve biases relative to flux tower derived GPP values. But maybe together these like kind of the literature out there starts to give a story that diversity effects may vary across ecosystem type and maybe also by the kinds of models that they're in. So over the past year and a half, we've been trying to take a look at this in CLM, answer some of these questions like if trait diversity, not just mean trait values, affects the sensitivity of carbon fluxes to drought, whether we observe diversity stability effects in simulations with higher functional diversity, and if those effects change by climate. And if you've seen versions of this presentation I've given like here last year or maybe at AGU, you might have seen me talk about some of these first two questions. But hopefully today I'm really excited to talk about kind of our answers to this third question of what mechanism was underlying the observed diversity effects that we kind of found in CLM, and are those diversity effects showing emergent behavior related to competition between PFTs. To answer these questions, we made use of the CLM5 parameter perturbation experiment. If you're familiar with some of these ensembles, this was Linnea's Wave 1 simulations. So 500 member ensemble over the historical period, perturbing 32 different traits in a Latin hypercube sample. So not min and maxes, but kind of doing all of these at once. For this analysis, we've selected 8 particular traits with a particular focus on 5 traits, which vary independently for each PFT. And those are kind of shown there on the right side of the screen. And importantly, between each of these 500 ensemble members, we're getting variation at the grid cell level in not just what the mean trait is amongst the coexisting PFTs there, but also variation in the diversity, the functional diversity within each grid cell. We're particularly interested in this output metric of drought sensitivity, which we're calculating here pretty simply as the percent change in GPP in the 3 most hydraulically stressed years compared to the entire simulation average. And we came up with a kind of data processing way to look at the effect of not just the traits, but the trait means and trait diversity effects. How we do this is we take at each grid cell, we transform kind of our input variables from just the raw trait values to the trait values in terms of their means and coefficient of variations, which is just a standardized standard deviation and is our kind of measure of trait diversity. So instead of training a Gaussian process simulator or another statistical method with just the trait values, we're training them with the grid cell scale, trait means, and trait coefficients of variation. And then this is allowing us to partition the variance in drought sensitivity between the means and the diversity pieces. and compute partial derivatives of drought sensitivity with respect to both the trait means and the trait coefficients of variation. And this kind of last like output piece from our analysis is the part that I'm going to be focusing on today, because this is what we're kind of calling our diversity effect from this analysis. So when we take an entire diversity effect, so this is the sum of the partial derivative of drought sensitivity with respect to each of the coefficients of variations of each trait, we start to see somewhat of a spatial pattern that looks like this, where we see where we see kind of decent biogeographic trends in the effect of functional diversity on drought sensitivity, where in warmer regions, this is mostly along an axis of temperature, where in warmer regions we see a positive diversity effect indicating that the ecosystems are less sensitive to the effects of drought, and we see these are kind of more resilient systems. But in more temperate and colder systems, we're seeing negative diversity effects, where increasing functional diversity tends to lead to ecosystems being more sensitive to drought and seeing larger decreases in the fluxes of carbon during drought. But as you can see, this is kind of one total diversity effect, and we're particularly interested in what of these kind of maybe which of these traits is driving this total diversity effect. And it was nice to go after Ben because I think he set up some of the important traits for me. So we find that Kmax is the kind of most important and really only trait that's showing a consistent effect on a consistent diversity effect in respect to drought sensitivity. So here in this plot, we're showing the distributions across space in the diversity effect of each trait. And Kmax is really the one that jumps out as having a consistent negative effect that is kind of strongly, significantly different from zero. Further, when we kind of pull this apart, what I was showing on the last plot was these total global distributions. But if we pull that apart into the individual biomes, we see that there is kind of strong between biome variation in the diversity effect of Kmax. You'll note that in most areas, it is kind of negative. So increasing diversity in Kmax leads to ecosystems that are more vulnerable to drought. But in some of our dry systems, in the subtropical deserts and the dry tundras, we see some positive effects here, although sometimes our samples get kind of small when we're cutting them down to the biomes in a sparse grid setup. And this kind of led us to like a couple of like lingering questions. So why is it that Kmax is the only trait that produces a strong diversity effect? And then why does that diversity effect vary across biomes? And to answer that, we stepped back a little bit, and as maybe Ben also foreshadowed, we see some strong nonlinear effects, especially with Kmax. So we looked at just the relationship between the Kmax trait, so not its diversity effect, but just the values of Kmax with drought sensitivity. And we noticed that this relationship is pretty nonlinear, with the strongest effects on drought sensitivity coming at low values of Kmax. And we realized this is going to have some numerical implications when we kind of sample across this function. So here I'm showing some idealized 1 PFT and 2 PFT scenarios and what might happen as we increase the functional diversity. So if we have our 1 PFT scenario with kind of an average Kmax value, we're going to get, a kind of middle of the road drought sensitivity value. However, if we increase our functional diversity, so now we're sampling from the more extreme ends of Kmax for 2 PFTs, we're not going to get an average drought sensitivity value that is the same. In this case, we're actually going to get a lower estimate of drought sensitivity than we would in our 1 PFT scenario case. But this isn't actually evidence of any like competition effects. This is just a like artifact of sampling across this kind of nonlinear space. This isn't anything like particularly novel or new. These kind of nonlinear effects are kind of ubiquitous across a lot of kind of land surfing modeling processes, but we're highlighting them here as kind of an important reason why we might be picking up diversity effects, even in cases where we don't have that strong a competition. We also, I think, can flip this, for instance, and we could have, if we had this relationship going the other direction, so a convex curve instead of a concave curve, we could find the opposite, where we're actually having positive effects of diversity, where the 2 PFT cases would be overestimating compared to the 1 PFT case. And so kind of our takeaway here is the shape of this relationship between Kmax and drought sensitivity really matters. And when we go back and when we find that relationship between Kmax and drought sensitivity at every biome, and then we fit a second degree polynomial to that relationship, we can pull out that coefficient on that second degree term, so this nonlinear component to it. And when we plot the diversity effect against that like nonlinear part of the relationship, we get a really good fit between basically the nonlinear piece and what the diversity effect was, which kind of leads us to indicate that, you know, this is kind of a numerical artifact and not necessarily any evidence of an emergent competition process or diversity effect in the model. A little bit more evidence for this is that none of the other traits have nonlinear relationships with drought sensitivity. So we weren't really seeing a lot happening with any of the other traits, and we think it's because they're relatively linear with drought sensitivity. So I'll kind of end it with some key takeaways here that the effective trait diversity that we're seeing in CLM, we think is a consequence of sampling across these nonlinear functions and not an emergent effect of competition. But this still might be meaningful from a calibration perspective. It can kind of tell us that we might need to consider only a smaller number of traits that we're actually going to have kind of diversity effects, so we might need to think about in our calibration efforts. But then I think it'll be interesting to redo this in like a FATES or CLM6 and beyond context, where there's going to be more explicit representation of competition in the model and where we might actually see some kind of interesting diversity effects that aren't just kind of these numerical artifacts. And then please check out, we have a paper that will be imminently out in Global Change Biology with Daniel, Linnea, and Anna that we'll dive into this more, but thanks.
Thank you. Cool. Time for a couple questions. Will, yes.
This is a really naive question, but why, whatever the red line was that goes the opposite way?
Yeah.
What PFT, or like, why does it do that? So go forward one more step.
Yeah. We think it's because in all the wetter biomes, there's a lot of basically punishment for having low Kmax values because there's basically they're going to be kind of more demand limited. So their water potentials are going to drop because they can't meet the atmospheric demand for water, even though there's not supply that's there to meet it. Whereas, so like the internal hydraulic structure is going to be like the thing that drives like drops of water potential. However, in like the drier biomes, they're going to be supply limited. So like it's going to be like a climate constraint is going to be the main driver of like the drops, whether the internal like xylem conductivity is able to deliver the water to the atmosphere is not as important as just like what the soil moisture state is. We think. So that's why we did the flip in that relationship is I think what's going on.
Is that a result of like the parameterization of PHS, or is that just like an emergent thing that comes out of?
I don't maybe know. I think it would be maybe we talk more about it because I think this might be like a good Daniel question. Because like I could hypothesize, and I think you would have like a better answer to it. I think just like the low Kmax values can be like really pretty tough on the plants, as opposed to like high Kmax values where they like even though they transpire a lot more water, that like never depletes their available water. So it's not particularly.
One more question. Yeah.
I guess I didn't memorize the way your map was, but do you see like places that we know are biomes with mixed vegetation pop out as benefiting most from diversity, like where all the savannas are and things like that?
Yeah, it's a little bit kind of tough because one of the like limitations we have here is like, for instance, the tropics have just one PFT there, so kind of inevitably we can't have a diversity effect in those areas because like the model just shows them as one PFT, so we don't have any avenues to like do this kind of sampling issues. So I think it is maybe interesting that like some of the drier areas are like popping out a little bit here, but I don't know if like the spatial pattern here is reflecting anything observationally, or it's just an artifact of like
how many DOTs are in each of these grid cells.
I'm excited to see this study of fates. So, okay. All right, thank you. All right, so last before our break, and we're going to hear from Gretchen Keppel-Alex. He's going to talk about regional GPP responses to, and so.
All right, thanks. So I'm going to be talking about some work that has been conducted by my graduate student, Maria Salazar. And I'm an atmospheric scientist, so I'm highly motivated by what's happening in atmospheric CO2. The growth rate of atmospheric CO2 is highly variable, and we've observed that the growth rate really depends on whether we're in El Nino or La Nina conditions. So this is a hot model diagram where we've got latitude on the y-axis, year on the x-axis, and you can see that the growth rate is increasing with time, in part because fossil fuel emissions are increasing with time. But the interannual variability, these times when you see like red and pink high growth rates, tend to be El Nino years. So from sort of a global or regional perspective, we can correlate the CO2 growth rate with things like temperature, and we observe that higher temperatures globally tend to lead to increases in the atmospheric CO2 growth rate. Similarly, low precipitation or low terrestrial water storage globally tends to lead to high CO2 growth rate. If you move beyond just using global CO2, like you can see on the left, and think about regional CO2, you can actually tease out that there's this covariation of drivers, including temperature and precipitation, that affect natural carbon fluxes, and then things like fire sort of act as a wild card that affect this CO2 growth rate as well. So, sort of the premise of this is just understanding what's happening globally is not sufficient to really get a predictive sense for how things like temperature and precipitation, or what a more El Nino-like world might mean for the global carbon cycle. So we're using the CMIP6 ensemble to try to tease apart regional responses to El Nino conditions. So we're taking 10 CMIP6 models, run in historical mode. For each model, we're calculating the Nino 3-4 index. So this is just an example from CESM. Positive values indicate that you're in El Nino conditions. Negative values indicate that you're in La Nina conditions. So we'll be regressing this index against climate variables and GPP across these models to sort of understand what is the emergent sensitivity to Nino 3-4 indices, or Nino 3-4 conditions. So here in this bar graph, we've got different Earth system models along the x-axis, and then the sensitivity of a carbon cycle flux to the Nino 3-4 index. So GPP is in green. You can see that most models have a negative sensitivity, which means that during El Nino, GPP is reduced relative to the climatology. Autotrophic respiration in light blue tends to follow GPP. Heterotrophic respiration shows the opposite response. It tends to increase during El Nino conditions, which might be due to generally hotter temperatures. But the bulk of the net response in gray is controlled by gross primary productivity. So that's what we're going to look a little more at. Ooh, these look pretty blurry. Sorry, guys. These maps show spatial variations in GPP with respect to the Nino 3-4 index. So here, greener colors would indicate an increase in GPP during El Nino conditions and vice versa. These are just three sort of representative models. And you can see that the behavior is somewhat variable, even in locations that from an observational perspective, we think we have a handle on. So for instance, the Amazon, you can see that CESM shows reduced GPP during El Nino conditions, but Meroc tends to show increased GPP during El Nino. So we, if you look across the whole ensemble, one of the things that we find is that there's really 4 regions, the Amazon and Southeast Asia within the tropics, and then Northwest North America and Australia in sort of the extratropics that comprise most of the global response. The global total is shown in the gray bars. So you can see that on average, there's a reduction of about 3/4 of a petagram carbon GPP per degree Celsius in the Nino 3-4 index. If you sum up what's happening just in those key regions, and we put Central Africa on here for sort of completeness around the pantropics, you get the X's. So you can see that in many models. Those regions tend to control the entire global response. But across all of these, you can see that the Amazon is really one of the key regions, and we're going to explore that a little bit more in this talk. So here, we're looking at the slopes of the GPP to Nino 3-4 regression within the Amazon. You can see that there's a few models over on the left-hand side that we've colored light green, where the spread within the region of the Amazon, you have some grid cells that are benefiting during El Niños and some grid cells that show a decrease. But across most of the other models, you see that really the majority of the grid cells are showing declines in GPP during El Niño. And if we look at plausible physical climate variables, precipitation, temperature, and radiation across the top, you see that most of the models are showing reduced precipitation. All of them are showing increased temperature, and most of them are showing increased radiation consistent with or decreased cloud cover and the reductions in precipitation. And if you look at the ordering of the response, you see that these look most similar to the precipitation response, right? Where the models on the left that show the smallest declines in GPP or even increases show the smallest reductions in precipitation. But when we look at the regression between GPP and these variables, you get sort of a different picture where the GPP precipitation relationship is pretty constant except for the Meroc model. And it actually looks a lot more like the ordering of temperature or radiation controls the overall GPP response to ENSO. So, sorry, I just said that. So what we want to do next is try to account for the covariance among all of these drivers, because they're all linked during El Niño conditions. So here we come up with reduced models. We fit a multiple linear regression coefficient for each of these 3 drivers, and then come up with a reduced model to figure out what each of these contributes to a partial sum of squares argument, and use that to come up with a weight. So you can see again for those same 3 models, there's a very distinct spatial pattern in terms of whether it's temperature, radiation, or precipitation that is the dominant control on GPP. If we start with BCC, which is maybe the simplest, you can see that within the Amazon, temperature is pretty much the whole show. If you go up to the top left, CESM, there's a little bit of codominance with radiation. And then if you look at Meroc, it's totally a mixed bag. So we can look at those for the Amazon on this diagram here, and you can see where each of these models sits in terms of the codominance between these different drivers. For total interannual variability in GPP, you see that the models really sit in this red and green part. Apologies to anybody who is colorblind. Very few models are showing this a dominant sensitivity to precipitation variables. What's sort of interesting is if instead of just fitting a multiple linear regression of the GPP variations to the interannual variations in these 3 drivers, but instead employ like the chain rule to isolate what the response is to only ENSO-driven variability, you can see that all of the models move closer into this red or temperature-dominated space. So we've been trying to understand a little bit more about why that is. And for the Amazon, what emerges is that the relative importance of temperature to downwelling long or shortwave radiation is organized along the moisture in the Amazon in each of these models. So we define this normalized moisture, which is basically how moist is the Amazon compared to global mean soil moisture, normalized by the spread in the 25th to 75th percentile soil moisture. So some of the models have more soil moisture than others. So we're really trying to sort of organize this in terms of for each model, how moist is the Amazon compared to other locations globally. And what we see is that the models that have a wetter Amazon tend to show more control by radiation. The models that tend to have a somewhat dry Amazon tend to show a lot of sensitivity to temperature. And in part, I think the mechanism there is that we're convolving temperature and moisture effects. That if you have a dry Amazon and you have high temperatures, your limited soil moisture is still going to go into transpiration to try to cool the plants. And so you're going to get this sort of apparent temperature stress, which is in part really a moisture stress. And I think, qualitatively, that's sort of consistent with the fact that we do see this nice ordering of how strong the precipitation sensitivity is in these models to the Nino 3-4, and the fact that we move from what looks like some radiation control of GPP when you're looking at total interannual variability to temperature driven when you're looking only at El Nino and La Nina driven variability, right? Like you have this drying, which moves all of these models to sort of a more moisture stressed Amazon, and the apparent importance of temperature increases. So what does this mean? I think like regional GPP responses to El Nino are driven by this complex interplay between temperature, radiation, and moisture. It's a function of the mean climate state and interannual variability with thereof. It seems like the mean moisture state in the Amazon is particularly important in determining whether it looks like interannual variability is driven by temperature versus radiation. And this is consistent with a paper by Paul Levine from a few years ago, who also emphasized that the apparent, if you look here in this figure, the drier Eastern Amazon shows sort of a stronger SST impact because you have this compounding influence of temperature and moisture. This doesn't seem to be the case in other regions that are strongly affected by El Nino. If you look at how the relative importance of temperature to radiation correlates with the regional moisture across the models. So, I think it again suggests that there's a really strong use for these models to try to better understand what we see in the observations when we see patterns that are apparent at global to hemispheric or zonal scales, that really different things can be happening on a regional basis. And these are nice tools to probe those. So I will take questions if there's time.
Thank you. Yeah, any questions?
One of your first slides looked like CSM had heterotrophic respiration decreasing in response to El Nino. Any idea what could cause that?
I think that some of that could be due just to the reductions in GPP. So one of the things that we've seen is that, actually I will show this, is that in CSM there's a really strong correlation between GPP and the respiration terms. And it's one of the reasons that CSM has pretty low interannual variability, because in the netbooks, it's because those things tend to move together. But I think less about like a climate sensitivity and more about maybe a greater GPP sensitivity for the respiration terms downstream.
Yeah, okay, so this is just a random observation, but when I was looking at the different Earth system models that got higher and higher emissions, like up to 3,000 petagrams of cumulative emissions, it was also MPI and MIROC that were continuing to linearly take up land carbon. So I'd be curious to look at what they're doing in Amazon, if there's letters in other models.
Yeah, so those are circled on this figure. Sorry, there's sort of 3 LR models that put circles around.
Radiation.
Yeah, so they're the most radiation sensitive and the less temperature sensitive. So it sort of makes sense that they're not going to be harmed as much by the increasing temperature as things are. And if it's getting if it's getting drier and lower cloud cover, then they're getting sort of a boost from the high radiation. So yeah, I think that probably is totally consistent with what we're saying. Yeah.
Okay, great. So now we can move on to, we have about like 8 minutes for open discussion. You can ask questions from the speakers in this last section, or just general, anything anyone wants to discuss. And please, online folks, either type in the chat or raise your hand, and we'd love to hear from you too. Yes. Dave.
I guess I'm just sort of wondering how Ben's talk and Gretchen's talk might intersect, right? The changing sensitivities in the Amazon due to parameters could alter the results, right? I'm seeing it just in general where's Ben at. Yeah, I guess, I mean, I'm really going to be interested to see what the regional responses are, because it's maybe not totally surprising that the global, when everything's averaging itself out. But in certain regions, or water limited regions especially, you might expect to see more divergence.
Yeah, we definitely see like large changes in the tropics. And so the largest changes that across unsolvent parameters generate are generally in the tropics. And so
And the other area is the one that Isla's been looking at, the semi-arid region. You guys are already thinking along those lines of seeing if there's anything in there.
yeah, and we noticed that there's some seasonality to like this changes in ET. I feel like that was very related to like some of what Isla, like in Isla's like connects paper.
And just to follow up on that, I think that's partly what Ben was trying to get at with deconstructing it into some kind of LAI and aridity space, is to see like some of these parameters are just influencing wet tropics with high LAI, and are there other parameters that seem like they're influencing other regions, rather than just staring at maps is maybe a bit more systematic way to go about identifying that.
And with that, it's a nice diagnostic, right? But it's for each different parameter perturbation. So then it becomes how do you then synthesize across?
Well, it looks pretty similar if you just keep the bin static from the default run. Yeah.
The change in ET.
No, not the changes. I guess I'm not sure what Dave's question is.
I'm not sure. I mean, I just feel like you can learn something from each one of those together, but then how do you get some sort of broader understanding of what's going on across multiple, each one, there's a different relationship for each parameter.
So we were thinking of trying to cluster them or do some sort of way of grouping them and thinking about mechanistically if there's something similar about the parameters that have influence in the same kind of region. Haven't gotten there yet.
Yeah, well,
I have another similarly opaque question. I don't know if it'll pan out, but I guess I was struck in Ben's talk, kind of we're focusing on the same regions for sort of similar mechanisms, and I'm curious if there's enough information from the PPE that Linnea did to start thinking about these coupling metrics, especially in a coupled model PPE, like what Ben's does, to think about getting in different regime states between those coupling metrics that anyone that's worked with Paul seems to be interested. I feel like there's kind of a bit of a divide between the land atmosphere interaction people and the parameter perturbation people. And it'd be interesting to start thinking about exploring that parameter space from as a unit, and others, from that land appling couple perspective. People.
I've been calculating some land atmosphere coupling metrics and across the PPE, and it's been a while, but my hand wavy explanation is that I don't think the PPEs really altering our coupling strength very much. Like we may need to think about smarter ways to design these things or different things.
But even in a couple of models.
No, in a couple of models different, right? Yeah, we have done that.
So I mean, analyzing what in Ben's ensemble would be more informative, right?
A fair amount of daily output. So we've had that in mind. So that would be a thing to look at.
I guess, also thinking about the questions that blinking. The Kyle was getting like, how do we use these ensembles? Like people are obviously using your ensembles a lot. And then you guys now are getting these coupled model ensembles, which I think they're super interesting resources that we probably don't. I'm on the train of like, we got to do more simulations, but we have a lot of stuff, and maybe just more people analyzing those would be interesting.
Yeah. Well, another thing that I thought of, and maybe I'm not interpreting this work correctly, but like seeing similar patterns in those LAI aridity spaces across parameters makes me wonder whether that's could be used as a tool to reduce the complexity or the dimensionality of the parameters. Because then if parameters are showing similar shapes across those that space, then maybe they could just be functions of each other and we wouldn't need to worry about. So identify the ones that have similar responses in that more dimensional space and try to see if they could be coupled versus varied separately.
Are you talking about for a PPE or just in the model itself?
Well, using the PPE to understand which parameters are really just functions of each other because they appear in that space similarly.
I'd want to think really carefully about whether there was any actual physical connection between the parameters because they could be totally unrelated to each other, but just have an impact on TET in similar places. And then you'd want to know across like lots of other dimensions, like area into PPE.
Well, I mean, ecologically, it's meaningful. So like plants kind of have traits together.
But I just want to double check that these traits actually do go together, I guess is what I mean.
Any other questions? Or we can go to break. All right, I'm gonna follow. Okay. When are we meeting?
3:10.
Be back here at 3:10.
Welcome back from break. Our first talk is going to be from Ying Sun.
Good afternoon, everyone. This is Ying. I'm an associate professor from Cornell University. So today I'm going to talk about a process, fundamental plant physiological process called mesophyll diffusion that is beyond the stomatal diffusion of CO2. So this work actually started from my PhD work back like 13 years ago. So what is mesophyll diffusion? Let's look at the CO2 transport from the atmosphere to the chloroplast where photosynthesis occurs. There are two steps. The first step is stomatal diffusion of CO2 that is characterized by stomatal conductance. The second step is really from the plant's intercellular airspace to the chloroplast. And this process is considered as the mesophyll diffusion of CO2. And we usually use mesophyll conductance, GM here, to represent this process. And of course, through stomatal conductance, there is also water out. So mesophyll conductance can impact photosynthesis. It is a strong barrier for CO2 availability for photosynthesis, and it can also impact water use efficiency. When we look at this pathway, diffusion pathway of CO2, these are typical values of mesophyll conductance, GM, and also stomach conductance. You can see that they have similar magnitude. But this process has been long overlooked in land surface models. To compensate for emission of this process, usually the VC max and other parameters are adjusted in order to compensate for the emission of this process. But is that sufficient? So we developed this first global mesophyll conductance model and implement that to CLM 4.5 13 years ago. So this framework is like we start from leaf level, we synthesize ACI curves and fit the parameters of mesophyll conductance and all the photosynthetic parameters across over 130 plant species around the world, so that we can develop a mixed mesophyll conductance model at the canopy top as a function of foliar mass per leaf area. And also we developed this vertical integration from leaf to canopy. Basically, the mesophyll conductance can decrease along the vertical canopy. And on top of that, we add this environmental stress, including temperature from leaf temperature and also soil moisture to downregulate this mesophyll conductance. And then we implement this whole process into CLM 4.5. So we have this structure update, but now we have a right process. We need to update the parameter as well, so that we update the VCmax and the Gmax values, also informed by our global synthesis of leaf level measurement. And we also make sure we have a numerical convergence once this new process is included. So the overall finding is that without explicit consideration of mesophyll conductance, the global CO2 fertilization effect of GPP can be underestimated. So even though we can have implicit consideration of mesophyll conductance by omitting this process but adjusting VC max, we can have the absolute mean magnitude of global GPP align with observations. But when we look at the long-term trend, we do see divergence. Okay, so extending from this work of mesophyll diffusion of CO2, we implemented this process to another two photosynthetic tracers. One is called OCS, the carbonyl sulfide. The other is carbon-13. So today I'm going to share the two stories of this two work led by my former PhD student Jia Meng. The first story is like, can we incorporate this carbonyl sulfide process into CLM in order to generate new insights of the global GPP in terms of the not only the global mean magnitude, but also the spatial variability. That's because since the 1980s, we have the impression that the global GPP is around 120 petagram carbon per year, and that number has been reiterated by recent remote sensing products, different remote sensing products. But actually, they share similar uncertainties because they upscaled exactly from the same set of occurrence data set. So they suffer from the same problem, which is spatial extrapolation. So now we want to see, okay, can we have independent insights of what is the global GPP without relying on the global eddy currents towers? And the second is the global historical trend of water use efficiency. It has been a huge debate of what is the pattern of historical water use efficiency at the ecosystem level. Is that continuing increasing over the past 5 decades, or it has already been saturated? And the different literatures reported different patterns. And the core issue responsible for such a debate is because we don't know whether the CO2 fertilization would win or the VPD, increased VPD would win, because the two have opposite effect on ecosystem water use efficiency. So here we try to utilize the carbon-13 discrimination implemented in COM along with atmospheric measurement of carbon-13 and also tree rain to see whether we can reconcile this historical pattern of ecosystem water use efficiency. So let's start from the first story. So why OCS? It is a mechanistic tracer for terrestrial photosynthesis. When we look at this figure, when we look at a CO2 amplitude, we can only measure the net CO2 signal, but this net CO2 signal consists of two opposite signals. One is the GPP and the other is ecosystem respiration. They have the opposite signs and they have seasonal offset. So it's very hard to disentangle these two opposite processes from this net measurable of CO2. This is different in OCS because the OCS concentration has a 6 order lower magnitude than CO2 concentration, and we do not have this respiration-like process. So the major sink of OCS is actually plant sink, and also the source of OCS is spatially separate from the sink because the source is mostly from ocean and industrial. So that's why OCS is really good tracer for photosynthesis because OCS share the similar diffusion pathway as CO2 here. From here, we can see from boundary layer conductance to stomachal conductance and to mesophyll conductance, and all the way to this GCA. The GCA is a reaction that can consume OCS. So if we can get this whole chain of conductance right, and this GCA is usually a constant, quite stable across globe, then we should be able to model OCS fluxes across globe, and with that, we can infer GPP. So the driving questions are, what is the impact of mesophyll diffusion on the global OCS uptake? And what is the GPP inferred from this global OCS fluxes? This is our technical workflow. We start from our mesophyll diffusion model, which I introduced in the very beginning, and put that into the OCS model, which has both vegetation and soil OCS flux. So here, we basically compare two scenarios. One is the mesophyll conductance implicit version. Here, this mesophyll conductance and also this GCA was combined as a single term here, GOCS. And this is modeled as a proportional or linear scaling with VC max. In the GM explicit scenario, we model mesophyll conductance separately using our model, and GCA was assumed as a constant, but also scaled with temperature. And then with OCS flux simulated, we can further derive OCS using this equation. So here, this F is vegetation OCS flux, also with CO2 concentration and also OCS concentration here, along with another variable called LRU, leaf relative uptake, which is a function of PAR, so that we can infer GPP fluxes from OCS fluxes. And we did different levels of model evaluation with all the possible data set available. And we implement this into COM5. So when we look at the OCS flux validation, we compare with in situ data at only two sites. One is in Finland, the other is at Harvard Forest. The dots are from in situ at the occurrence-based measurements of OCS fluxes. And the blue is the GM explicit simulation, and the red is GM explicit simulation. We can see that in terms of both peak magnitude and seasonal timing, the GM explicit simulation is doing much better. When we look at the global simulations, here the maps shows the differences of plant OCS fluxes simulated between the explicit versus implicit processes. So we can see that the percentage difference can be up to 50% of the global regional OCS fluxes, and such differences are seasonally asymmetrical. So that means we cannot really assume a static OCS conductance simply as a function of VC max. We need to have a dynamic mesophyll conductance model inside the global models. So when we look at the global GPP inferred from OCS fluxes, let's first look at the global OCS based estimate, which is around 157, much higher than our traditional impression or traditional belief of the global GPP. Of course, we do have uncertain ranges here. But this is highly consistent with independent approaches, including the oxygen-18 isotopes here. This was published by Ralph Keeling's group many years ago, showing this 150 to 175 petagram carbon per year, consistent with our approach. And here, these two approaches are totally independent. And also another independent approach was from, I think, PNL. They were using the soil respiration-based approach to back calculate GPP, which is around 150. So these three independent approaches are highly consistent with each other. But when we look at the satellite optical remote sensing based approach, no matter which products you are looking at, it's bounded in this range. When we look at the satellite SIF based product, it's around 135. So where are the spatial discrepancy coming from? It's actually from the tropics. When we look at the MODIS GPP, GOSIF, and FluxSat and the FluxCom GPP, they are all these are the most widely used benchmark dataset. When you look at Amazon and the Congo, you see quite spatially homogeneous GPP, which is actually not the case when we look at the OCS simulations. We do see much higher productivity in the Western Amazon and lower productivity in Middle and Eastern Amazon. And this Western to Eastern gradient is highly consistent with plot level based measurement reported, I think, a couple of years ago by a group in UK. So let's move to the second story. How do CO2 fertilization effect and also VPD counteract, and how do they jointly shape the historical pattern of ecosystem water use efficiency? When we look at this figure, maybe let's look at this first paper here. This paper shows the global ecosystem water use efficiency is already saturated because of water VPD. So the water use efficiency at ecosystem level here is calculated as a ratio between GPP and ET. When we look at this figure, we compare this satellite-based product, the red curve here, versus like tree ring-based analysis from yellow and green. They show very different patterns, right? So why satellite products give you very different patterns from other measurements? Because neither GPP products or ET products from satellite are reliable. And when you calculate the ratio, the uncertainty would propagate to this ecosystem water use efficiency. So our approach here is that, okay, can we constrain this ecosystem water use efficiency with observation as much as possible? So we rederive this equation by parsing ecosystem water use efficiency into three components: the intrinsic water use efficiency, which is the ratio of GPP to star-metal conductance, and the VPD here, and also T to ET ratio. Because VPD, we can have relatively more mature product, although not perfect, but relatively more mature observational products. And the IWE can come from tree ring and also the carbon-13 measurement from the atmosphere. So here, the two questions, okay, what is the historical trajectory of water use efficiency, and what are the relative roles of VPD versus CO2? So the step one is to infer the global intrinsic water use efficiency using the atmospheric carbon-13 measurement and also tree ring. And the step two is to infer the global ecosystem water use efficiency using this equation. So first we compare so we use this equation from Ralph Keeling. This is the CO2, the delta 13 discrimination. So here GI is actually GM, the mesophyll conductance. So we put mesophyll conductance here in this equation. And when we compare model simulation, the y-axis versus x-axis from the observation, they align very well with each other. So now we have three independent approaches. We have global simulations, we have tree ring, and we also have this global integrated atmospheric carbon-13 measurement. So here we show consistent results, which is that there's a decelerating of the ecosystem water use efficiency, but it was not saturated. When we look at this regression slope of ecosystem water use efficiency against the CO2 across 3 different time periods, we do see the slope is decreasing, but it is always positive. And this positive slope continue into the future. When we look at the intrinsic water use efficiency, surprisingly, they are quite stable because this is primarily driven by CO2 concentration, CO2 increase. Only the ecosystem water use efficiency can be regulated by increasing VPD. So here, 2 pieces of story. The OCS-based global GPP aligns closely with the independent measurement, independent approaches that are totally independent from the eddy covariance-based upscaling. And also CO2 outweighs VPD to control the global ecosystem water use efficiency. Final thought is that we try to seek multiple independent of evidence. If they converge, we have trust. But when we use like a data set that are not derived from independent approaches, then we might see, okay, we have like a pretty tight observational boundary, which may not be the case because the different products share the similar uncertainty. Yeah, that's all I have. Thank you.
Great. We should move on because we're behind time. Okay.
Okay, sorry. Yeah.
Thank you. Okay, great. Up next, we have Amy Liu talking again about stomatal functioning, this time without transpiration.
Cool. Hi, everyone. It's great to be back in person here at the Mesa Lab. So yeah, as Abby said, today I'm going to talk about how stomatal function can shape evapotranspiration, elevated carbon dioxide world. And this was funded by the NSF. And as Ben has so nicely summarized earlier in his talk, predicting understanding drivers of evapotranspiration is challenging. And there's been like a huge body of literature trying to understand ET and predict future ET. And I'm going to add to this body of literature by trying to understand or quantify stomata effects on ET under elevated climate. So to start, delta ET full will be delta ET full will be our full response to elevated carbon dioxide. And we can divide that into 2 components, the radiative component and the physiological component, so ET rad and ET phys. And we can further divide ET phys into a leaf area driven component and a small conductance driven component. And so just a little quick schematic where leaf area represents like total transpiration, because I should start with the stomata first. Stomata control the rate of transpiration, where when they're more open, more transpiration is occurring. So they control the rate of transpiration, while leaf area, if there's more leaf area, then there's more stomata under the assumption the stomata density is pretty consistent. Can you guys hear me? Sorry. Higher. Oh, this one. Okay. So sorry. Technical difficulties. Okay. Well, the leaf area controls the total transpiration, where if there's more leaf area, there's more total transpiration. And within the stomata-driven ET, under elevated carbon dioxide, both leaf area and stomata are expected to respond to this change, where carbon dioxide fertilization will increase leaf area, increasing total transpiration, while stomata are expected to close, since they don't have to open up their stomata to uptake the same amount of carbon dioxide, which would decrease the rate of transpiration. So we see that stomata and leaf area have competing effects on future ET. And if I focus on the stomata, for a second, I said earlier that the aperture of the stomata is inversely proportional to carbon dioxide. And it's also controlled by how a plant chooses carbon gain against water loss. And within CLM, we can sort of control that with this metal and slope parameter called G1M. And this G1M, estimated across observations, has a pretty large range across different PFTs. So this is just a plot showing the possible ranges of G1M according to observations for every PFT within CLM. And for our experiments, we perturb G1M to this low and high value and see how evapotranspiration would change. So a low G1M corresponds to more close stomata or a higher water use efficiency. You can think of like that intuitively, while a high G1M corresponds to a more open stomata or a lower water use efficiency. So returning to my flow chart, I'm adding this like blue and orange ET low and ET high, which corresponds to stomata-driven evapotranspiration with a different Mendelian slope, so lower or higher Mendelian slope. And then to isolate all of these components within this flow chart, I'm essentially just comparing a bunch of simulations over different values of atmospheric carbon dioxide and taking that delta to get how much the delta ET for each of these components. Okay, so to start off broad, I'm going to look at the full radiative and physiologically driven evapotranspiration response to elevated carbon dioxide. And essentially what I'll show here are lines representing each of those delta ETs. And on the, it's like a histogram, but instead of like count or density on the y-axis, I have a fraction of land area. So you can think of it like, what is, how much of land area has that certain change in ET? And if I look at full, so I also have the 0 line in dashed magenta there. So if I look at the full response, we expect that ET would increase under elevated carbon dioxide. And so since most of that line is to the right of the magenta dotted line at 0, and the little line on top of each graph is like the 20th to 80th percentile range. And then if I were to add on the radiatively driven ET line in red there, we would see that the rad increases ET and is pretty similar to the full response. So it's a pretty large contributor to the full ET response to elevated carbon dioxide. However, the phys response is also important. It also, which is this green line here, we see that the physiologically driven ET response is also like largely an increase in evapotranspiration, but just to a smaller magnitude than the radiatively driven response. But it's still important because around 25% of like the global full response is from phys. Okay, now I'm gonna like look at that green line and put it on a new X and Y axis, so I can compare it against the components of like how much of it's leaf area driven and how much of it's stomata driven. And so introducing it one by one again, this purple line is the leaf area driven ET response. And we can, how you can interpret this is that in the absence of stomata response to elevated carbon dioxide, if we were to just look at leaf area changes, then leaf area changes drives an even larger increase in evapotranspiration than the total phys response. And if I were to introduce the stomata-driven ET response, which is this turquoise line, we see that as we kind of expect, the stomata has an opposite response compared to the leaf area response on ET, where this turquoise line is largely in this negative delta ET range. Sorry, let me take a breath. I'm like zooming through. Okay. So these leaf area and LAI have an opposing responses. LAI technically has a larger magnitude of ET response compared to stomata, but it's still pretty important. In fact, in around 15% of land area, the effects of stomata on ET are larger than LAI. And, but I'm gonna now highlight this like turquoise line and look at alternative like possibilities of stomata-driven ET response with a different Mendelian slopes or different water use efficiency. So now I'm taking that turquoise line and again putting it on a new X and Y axis, so I can probably display the other possible stomata-driven ET response, which is this like blue and orange line. Blue corresponds to low Mendelian slope, orange corresponds to higher Mendelian slope. And what we see here is that this like distribution spread is a little bit wider than the turquoise line when we have a different Mendelian slope, and that the distribution of the blue and orange line are shifted a little more to the positive side. If you see here, can you see my mouse? Okay, great. You see this like, this turquoise line kind of ends around right before 2 watts per meter squared, while this blue and orange line extend further. So it turns out that like small uncertainty driven evapotranspiration response is pretty large relative to the stomata ET driven response. And if we take these lines and just look at the additional ET response due to stomata uncertainty, we will get this plot here. So I think there's like a couple interesting things, like two interesting points to see from small uncertainty influences on ET. One is that this additional evapotranspiration response from small uncertainty is pretty comparable to like the leaf area driven response, which is, I'm putting this purple line back on for leaf area driven small response, where there's like this overlapping area, here, where the small driven evapotranspiration response is actually greater than the leaf area driven evapotranspiration response in around 34% of land area. So I think trying to understand small uncertainty and where it is most sensitive is important. And the second interesting feature that we saw was that no matter how we perturb G1M, whether we perturb it a lower value or higher value, we get the same sign of additional evapotranspiration response, which is an increase. So these are spatial plots of the additional ET response to elevated carbon dioxide due to a perturbed G1M. Low is on the left here, and then high is on the right. And green corresponds to an increase in evapotranspiration, and brown corresponds to a decrease in evapotranspiration. And like, while spatially they are kind of different, it's like green, like it's largely green. We see increases in additional evapotranspiration, ET response due to different reasons. For the high G1M case, because we're forcing the stomata more open from the default G1M within CLM, the rate of transpiration, is that there? Okay. The rate of transpiration increases, so then that just increases ET, while for a low G1M response, plants are transpiring less with a more closed stomata, which means they're less water stressed on their future climate. And then so they grow more leaf area in general. And when they increase leaf area, total transpiration increases. Okay, so I realize I kind of blew through that since I'm out of breath. So I'm going to go over my summary more slowly. So first, we saw that the physiological influence accounts for around 25% of evapotranspiration response to elevated carbon dioxide. So ET phys is around 25% of ET, delta ET full. And we saw that physiological influence is largely driven by the leaf area growth effects on ET, and that stomata and leaf area have opposing effects on evapotranspiration under elevated carbon dioxide. In addition to that, from the stomata driven ET response, we see that the small uncertainty actually has a pretty large effect on evapotranspiration or changing small driven evapotranspiration, and its additional response is actually greater than the leaf area growth effects on ET in around 34% of land area, and that both small uncertainty in either direction of high and low G1M causes increases in evapotranspiration under elevated carbon dioxide for different reasons. Okay, cool. Thank you. So happy to take.
Yeah, let's do one question while we're changing over to the next talk.
So I guess I'm surprised that the delta ETGS extends past zero. Why? Like, can you explain what would cause it to be greater than zero, the GS effect?
So for this plot or
or that, yeah, the green, or no, I guess. Well, yeah, any of the ones in these green lines. I would expect it all to be the left at zero, but some of it's the right.
Yeah, I haven't actually explored like exactly what might be causing some increases in ET. We've mainly been trying to disentangle like why some places have a larger ET response or are more sensitive to small uncertainty than others. But that is an interesting point that I think, I should get my reader. Yeah. We actually write more of it is really interesting. Yeah. In terms of hypotheses, mainly I've been trying to understand why some places more sensitive to stimuli than the area, which if anyone has thoughts, I would gladly welcome them because we've looked at quite a bit of different like Whittaker plots or aridity, leaf area, drawing those like that threshold of difference for sensitivity. I'm not answering your question, I'm asking you a question. Yes.
Okay, great, thanks. Next up, we have Rachel Hallmark talking about C4 photosynthesis at neon grassland sites.
Thanks, Abby. Yeah, my name is Rachel Hallmark. I'm a graduate student at Colorado State, and I'm really excited to talk to you about this work on evaluating C4 photosynthesis at neon grassland sites. Starting with framing C4 photosynthesis in the Earth system, C4 photosynthesis accounts for about 20% of global terrestrial GPP, which is kind of a lot as it is, but it's also a lot when you consider that C4 plants only make up about 5% of total plant species, so a really disproportionate effect on total GPP compared to like the portion of plant species that they make up. Due to this large influence on terrestrial GPP, understanding C4 photosynthesis is really important for understanding climate carbon feedbacks and global energy fluxes. Additionally, a lot of important agricultural plants like corn and sugarcane use the C4 pathway, so it's really important to think about C4 photosynthesis when we are thinking about agricultural productivity. This figure on the right is showing the fraction of vegetation cover that is C4. The main thing I want to point out here is that the higher fraction of vegetation cover that is C4, represented by the darker red colors, is seen in regions that are pretty typically hot and dry, which makes a lot of sense when we think about the differences between C3 and C4 physiology. We generally expect C4 plants to be more CO2 and water use efficient than C3 plants. This is kind of illustrated by this diagram on the right. That's a little bit of a simplified representation between the differences of C3 and C4 photosynthetic pathways. And the main thing that I want to highlight here is that C4 plants can concentrate CO2 around rubisco, which is their CO2 fixing mechanism, in bundle sheath cells. So they're not as reliant on ambient CO2 as C3 plants are, which are kind of just relying on whatever CO2 is around through stomatal diffusion to do photosynthesis. So even under low CO2, C4 plants can usually still maintain enough CO2 in those bundle sheath cells to be pretty efficient at photosynthesis. And this phenomena has been pretty widely studied. This is from a meta-analysis of free air CO2 enrichment experiments or FACE experiments that's looking at the mean yield response between a variety of C3 and C4 crops in response to elevated CO2. And you can see the box highlighted in green. All C3 crops increase yield in response to elevated CO2, and C4 crops didn't really increase yield in response to elevated CO2, which is expected because of that CO2 concentrating mechanism. Because of that mechanism, we also expect C4 plants to be more water use efficient. Again, CO2 and water exchange are really linked through stomatal conductance, so C4 plants are able to have enough CO2 to do photosynthesis without opening their stomata to lose water. So because of these differences in physiology, we would expect C4 plants to be better adapted to hot and dry environments, and C3 plants to be better adapted to cooler and wet environments, which is kind of what we saw in that map earlier. Switching to thinking about C4 photosynthesis in CLM and Earth system models, despite its importance to terrestrial GPP, C4 has historically not been really well represented in Earth system models. The model that CLM currently uses for C4 photosynthesis is the Colette's et al. Model that was originally parameterized for corn. Corn is a really important C4 plant, but not all C4 plants are corn. And this model has never really been evaluated in natural systems, which is a really big motivation for this project. So the first objective of this project is to evaluate how well CLM simulates GPP at C3 and C4 grass sites relative to neon observations. And then the second objective is to see if CLM captures expected physiological differences between C3 and C4 grasses under modified environmental conditions. All of the simulations that I'll be talking about today were run in satellite phenology or SP mode. Probably a lot of people know about SP mode, but very quickly, in SP mode, vegetation phenology and LAI is prescribed for MODIS satellite data, so those things aren't really changing with model inputs. There's also limited nutrient cycling, so the only carbon cycling that's really happening is photosynthesis. So it's a more quote unquote simplified model as opposed to like biogeochemistry mode. but this really helps us to isolate photosynthetic responses from other downstream feedbacks like nutrient cycling. So first objective, comparing CLM GPP simulations to neon observations. The workflow for this is pretty straightforward. We start at a neon grassland. So all of these are single site simulations run on either a C3 or a C4 grassland. We run a default simulation. This gives us some sort of output, and then we compare this to neon observations. And when comparing this to neon observations, we see that CLM pretty consistently overestimates GPP at C4 grass sites. So this is looking at the anomaly between neon observations, which would be represented by the 0 on the y-axis, between CLM simulations at C3 and C4 grass sites. So you can see in dark green, the C4 grass sites, it's the average of all C4 sites. Pretty much all those values fall above that 0. And then for C3 grass sites, we see that CLM slightly underestimates GPP, but it's not necessarily as strong of a pattern as we see at the C4 sites. Another way to look at this, just looking at summer productivity, a lot of winter productivity values are 0. So just focusing on the summer ones, comparing simulated GPP and observed GPP with the 1-to-1 dashed line being where simulations would directly match observations. We again see that most of those values for C4 sites are falling above that 1-to-1 line, and some of the values for C3 sites are falling below that line. But again, not as strong of a pattern as we see with C4s. All right, so moving into the second objective, which is assessing whether CLM captures these expected physiological differences between C3 and C4 grasses. Again, we expect C4 grasses to be more water and CO2 efficient than C3 grasses. So again, we're in satellite phenology mode. We're starting at a C3 or a C4 neon grasslands, and then we modified 3 different environmental conditions. The first was to increase CO2 to 550 parts per million, which is what a lot of FACE experiments have done. Second, lower CO2 to 280 parts per million pre-industrial levels. And then the third is to impose a year-long drought with half precipitation. Again, run all these simulations. They give us some sort of different outputs. We then compared all of these modified simulations to the default simulation, and then compared all simulations to neon observations. So starting with the GPP response to modified CO2, this plot is looking at GPP percent change between the default simulations and the 2 CO2 treatment simulations. So that 0 on the y-axis would be the default simulation, and the high CO2 treatment is in pink and the low CO2 treatment is in blue. And oh yeah, I will mention for the rest of this talk, I'm just gonna be focusing on 2 neon sites. So this is the first site. This is the C3 grass Dakota Coteau field site in central North Dakota. So we see that the high CO2 treatment pretty consistently increases GPP. The low CO2 treatment pretty consistently decreases GPP. This is a pretty expected response. We saw that C3 plants are pretty sensitive to changes in CO2, so this is kind of what we would expect. There is a weird spike in both directions in the last year of the simulation, so that could be some environmental influence that is worth looking into. And then moving on to our C4 site, this is Konza Prairie in eastern Kansas. Kind of as expected, we don't see a very strong response in the C4 treatment to high CO2, but we see a pretty strong response to low CO2 at the C4 site, almost like stronger than the C3 site, which again, really surprising. We would expect these C4 plants to be pretty efficient at using CO2, and we would not necessarily expect that a reduction in the 280 parts per million would decrease GPP by that much. And then looking at the results of our droughted experiment, so this was with a year-long drought. Again, starting at this C3 site, we see that drought pretty consistently decreases growing season GPP, not unexpected for C3 plants. They are pretty sensitive to water and CO2 changes, so kind of expected. And then moving on to our C4 site, we again see that this drought treatment pretty consistently decreases growing season GPP. Which again, a little bit surprising at a C4 site. They should be a little bit more water use efficient, but this was like a year-long drought. So it could just be like, that's too much drought stress and they kind of lose their water use advantage under those situations, especially if this site was already water stressed. I'm not exactly sure if it is, but I wouldn't be surprised if it was. I also want to point out here that it kind of looks like there's a strong signal in percent change in the winter at our C4 grass site. This is just because winter GPP values are already really low. So any difference kind of makes the percent change really big. So the absolute GPP difference in these is like less than 0.1 gram of carbon per meter squared per day. So not necessarily super ecologically important. right, so kind of summarizing all of the experiments compared to NEON observations. These plots are looking at the annual average GPP across the 4 years we're looking at. The error bars are plus or minus 1 standard deviation. So representing the interannual variability of GPP. Starting again at our C3 grass site, we see that the NEON observations have a higher GPP than CLM. So CLM is underestimating GPP at this site, which is pretty consistent with what we saw in our first objective, when we looked at all C3 sites compared to NEON observations. Looking at our high CO2 treatment, we see that it increased GPP a little bit compared to the default simulation, but still underestimating it compared to NEON. And then when we move on to these more like environmentally stressed scenarios, such as low CO2 or drought, we see that again, CLM is still underestimating compared to NEON, which makes sense. There's a stress applied, but it brings it down a little bit compared to the default simulation. So overall at this site, CLM is underestimating real world GPP, and environmental stressors kind of make that difference a bit bigger. So moving on to our C4 site, we start out with seeing that the default CLM simulation is pretty substantially overestimating the NEON observations, which again agrees with what we saw in our first objective, looking at all of those sites, so that's not super surprising. When we change CO2, not much of a response. It's still overestimating compared to NEON, but it didn't really change much to the default. Again, we don't really expect C4s to have that strong of a response to modified CO2. However, when we get to the more stressed simulations, we see that the low CO2 simulation does decrease GPP quite a bit compared to the default, and actually brings it a bit closer to NEON observations. And it looks like the droughted simulation might bring GPP a little bit below NEON observations, but it's really hard to tell because there's quite a bit of interannual variability. Kind of rush through that. Anyway, so thinking about our first objective, we saw that CLM pretty consistently overestimates GPP at C4 sites and slightly underestimates it at C3 sites. And then when we modified some environmental conditions, we surprisingly saw that the C4 site was more sensitive to low CO2 than the C3 site. We would not expect that. They should be more efficient. But it was less responsive to higher CO2, which was a bit more of an expected response. And then we also saw that simulated environmental stress, such as low CO2 or drought, lowered GPP for both PFTs compared to default simulations, but they had opposite biases. So at the C3 site, with these environmental stressors, GPP gets further from observations, but at the C4 site, the GPP under environmental stress, GPP actually got a bit closer to observations. And some future work I would like to do is expand analysis of these modified simulations to other sites. There's a few more NEON sites. This was really only focusing on 2 that I thought were kind of representative of what I was seeing. And I'm hoping that once I expand this analysis to other sites, we'll be able to explore some patterns between similar PFTs and maybe make some PFT level conclusions, not just site level conclusions. And then I also think it would be worthwhile to investigate environmental differences between sites. NEON sites are all over the country. Their baseline environments are very different from one another. So there could be things like abnormal drought or abnormal heat that are influencing GPP other than just what we're seeing in the model. Thank you.
Okay, we have time for one question.
Yeah, this work. I just wonder, like, what is your interpretation of why you have underestimation or overestimation for C3 versus C4? Is that because of phenology, or is that because of like VC max or something else?
Yeah,
so that you can improve.
Yeah, thanks. Good question. I guess at C4, I'm not so sure about C3, but VC max is fixed for C4 photosynthesis. So if like VC max is not responding to lower CO2 or other environmental conditions, then it's just assuming that like Rubisco has enough CO2 at all times to be productive, and that could be like a cause for overestimation, but not exactly sure for C3. I kind of got to dive into the model equations a little bit for that. So thank you.
But I feel like the phenology part might also contribute to the bias, because if you run SP mode, is that from satellite data or is it from in situ like LAI?
It's from satellite data, so it's like observed LAI. We actually we started running with BDC and have some kind of funky results, which I'm happy to discuss later when we have more time. But yeah,
All this phenology also has a lot of bias for those classes.
Yeah, that's true. Yeah. Thanks.
Thanks. So next up we have Thomas Kabu. Thomas, can you share your screen? Great. And you can go ahead and get started when you're ready.
Hello everyone. You can hear me? Can you hear me?
Can hear you.
Okay. Good afternoon, everyone. My name is Thomas. I'm a student at Auburn University. And today I'll be talking about multi-site calibrations of CLM6 for water and carbon fluxes, emergence of parameter coherence. And I would like to pass my appreciation to my advisor, Dr. Sajiv, Dr. Kalin, Dr. Yang, Dr. Will, and help from Dr. Hawkins. Thank you so much for helping me with this research. It's not yet complete, but I'm happy to present some of the findings and some of the exciting results that we have. You're welcome to follow through. So the motivation of this study is that many model parameters controlling photosynthesis, tomato conductance, and soil plant hydraulics are poorly constrained at ecosystem scale. And there are large within PFT, within plant functional types variations. For example, VC max, well-known parameter varies by a factor of 2 to 3 within the same PFT. And these variations or these changes create uncertainties that propagate to ecosystem productivity and carbon water flux estimates. And much of this variability or much of these changes is driven by climate, soils, and species by a factor not captured by global defaults. And also the other thing that attributes to that is that we use simplified processes in these models to represent these actual processes. And then the fixed PFT structures impose rigid behaviors that limit representation of physiological diversity and altering water and carbon coupling in these models. And some of the challenges and opportunity that is that calibration most of the time relies on global or site-specific defaults, and that rarely captures trade distribution. And also, like in Earth system models and land service models, they are large models representing large processes, and calibration is also computationally constrained. And one of the things that is mostly used is single objective optimization, where people only focus on a single flux like GPP, and this enforces or leads to some trade-offs in that you are optimizing for a specific flux, and you might end up affecting other processes. And one of these was really well captured by our previous research whereby we did optimization, but based on point scale calibrations, where we just looked at individual sites. And we realized that some of the tuning that we did to the parameters, instead of us getting a well-representative value, some of the parameters were kind of like compensating for these limitations in the model representation. Like we see the leaf carbon-nitrogen ratio in the tall and OSPS sites, which are middle leaf deciduous vegetation, they kind of like compensated and they decreased the value so much. And on the other side, there is the broadleaf deciduous, that is the ONRL. It also increased to kind of compensate for the fluxes. And parameter equifinality obscures physically plausible combinations. And then we also have identifiability issues where multiple parameter sets fits one side, but also they fail to scale across scales. So in this work, we are focusing on trying to borrow some from hydrology. That is, in hydrology, we have the sequential uncertainty fitting algorithm, that is the SUFI framework, which has wide applications in calibration and uncertainty analysis. And we are bringing that in because it's going to help us iteratively constrain parameter ranges based on model data mismatch and using key performance indicators. That is, one, it looks at the proportion of the observation data points that fall within the 95% prediction uncertainty band, and also looked at the average thickness of the 95% prediction uncertainty. And it's also computationally efficient. It kind of doesn't lead to development of a different processing framework. You can fit it well into perturbed parameter ensembles to help you constrain or look into varying several parameters and the combinations and try to find the most optimal ranges of the parameters that are doing well for against observation on data points. And this is the basic workflow of the SOFI framework. You have your initial ranges, you do sampling. Most of the times they use the Latin hypercube. That is what we are using for these experiments. Also, you run your simulations. And then here you define your convergence criteria. That is the objective function. And if you achieve your, if you, the objective, the convergence criteria is met, then you have your final parameter ranges plus uncertainty. If not, you repeat the iteration. And this is our kind of the adopted framework for the CLM. It's kind of a little bit messy, but I'll rush through it. The first thing that we do is we define our objective function. And at this part, I spend a few moments to just explain that for this experiment, we are using several sites. I will show them in the next slide. And we are focusing carbon and water fluxes. And our main variables are net ecosystem exchange and evapotranspiration. And the other thing that we are doing is we are not looking at the entire time series of our data sets. We are compartmentalizing that data sets into different seasons of the year, and we are calibrating for each season. So at the end of the day, we have 4 compartments for each variable. And when you are also having 2 variables, that means we have 8 compartments. And this is the scoring that we use. We are using the Klein-Gupta efficiency, which is a very good metric that combines variability, correlation, and bias. And we're using that also like 1 minus the Klein-Gupta efficiency to use it as a minimized objective function. And then this is how we are computing the final, the composite score, where we are kind of applying the uniform weight for both the variables, that is NE and ET, but we are trying to give more weight to the growing season, that is the MAM and the JJS seasons. And the workflow just follows like what I had previously explained. You do the sampling, you run your simulations, compute your objective function, compute the factors, and then if your criteria is satisfied, you proceed to uncertainty analysis and you obtain your parameter ranges. If not, you update your parameter ranges, and then you resample again and you repeat the process. But for this case, in our approach, that's why I have this one dashed. The first phase of this work was using the perturbed parameter ensembles to run the first phase, and we are proposing, or we are thinking of running the proceeding phases using machine learning approaches, which we have not done for this work. So these are the number of parameters that we are using. We have a total of 70 parameters that we are using for this experiment, and some of those, they are highly correlated, that we group them to about 56 parameters that we use. And we are running 14 sites, that is 6 needle leaf sites and 8 broadleaf sites. We're doing 1,000 simulations using Latin hypercube sampling. And the setup includes doing a spin-up using the Plumber-2 protocol, that is initializing the CLM using the pre-industrial CO2 and nitrogen deposition. Then we do transient runs from 1850 to 2018. And then we do production runs, that is the final CLM simulations from 2018 to 2024. And this map shows the distribution of our sites. We see the square red black dot, those are the broadleaf sites, and they are very well distributed on the eastern United States. But the needle leaf sites, they are kind of, we only have 3 within the southeastern United States, and we have 2 on the western United States, and we have 1 in the middle. And that probably would be very interesting to look at how the model works when we are trying to find a single parameter that represents these varied ecoclimatic domains. So some of our initial results, we are going to present some of the results here, and we see from all the 8 sites from the broadleaf deciduous ecosystems, the overall improvement using the KGE and the composite scoring was 13% of improvements. And we can see that is very well represented from the latent heat, where we have all the sites, that is 8 of 8 sites, shows very significant improvements. And we can see the concentration of the default values from CLM, and these are the optimized values that are very close to the reference. And the correlation, also the metrics here, like they show improvements. Correlation improves from 0.78 to 0.881, a total increase of 0.028. And also we see the standard deviation ratio also improves, and the centered root mean squared differences decreases, which is a good sign. But when we look at the net ecosystem exchange, kind of the results are not looking like very flashy as well as the LE. We see like kind of most of them, they don't. We don't see like any significant differences between the default and the PPEs. But we also see improvements in 5 out of 6 sites using the overall KGE metric. And we didn't use the GPP during the calibration, but we used it like to test like, yes, we've calibrated for NEE and ET, what happens to the GPP. And we see also like a very positive result from the GPP, where we also see like it improves overall like across several of the sites too, with some very good metrics as well. And then when we come for the needle leaf ecosystem, and I showed that in the distribution of our sites, we have 3 in the southeastern United States and 1 in the middle, in the central, and then 2 on the western, which we think maybe that brings in the challenge in calibrating. Using the KGE metric shows 5% overall improvements. But when we look at the medians for these, especially for the latent heat fluxes, we don't see like there are not significant differences between the default and the PPE. And also like that is also like seen from the Taylor plot, where the improvements they are not very significant, but also it doesn't worsen. The simulations from the CLM. And we also wanted to look at the seasonal fluxes and scale score, that is looking at the overall like the demands, like how the variations or how the model captures the observed. And we see again, we looked at 2 representative sites. One is the tall site for PFT1, that is needle leaf ecosystem, and the GRSM site for broadleaf deciduous temperate. And for these, we see like the improvements are very well defined. We see by default CLM underestimates evapotranspiration, but then we see after calibration, the PPE or the CLM now is able to capture well the observed latent heat, and also the same for GPP. But for PFT1, the tall side, again the improvements are not very flashy. But yeah, we see the model also like does some slight improvements. And the other thing that we wanted to look at is comparing like now lumping all the data sets together. That is the daily data model versus observations using the X-bins. And X-bins is kind of like divides the graph space into hex bins and presents data sets in those bins. That is, we have high values that represent like more where the more data sets are. The black line is the reference point, that is the observation, and the red line is the simulated. And we see again like very well the default underestimates latent heat. This is for latent heat, and the PPE tries to reduce that bias. And this is for PFT1 for the 3 variables, that is for latent heat, NEE, and GPP, and it's still the same pattern, whereby the default and the PPE, they are not very significantly different, even though the PPE tries to slightly improve that. But for the broadleaf deciduous, we see like some very good improvements in the model. And the other thing that we did was sensitivity analysis, and we see a small subset of parameters that show consistently high sensitivity. And for PFT1, we have the leaf dimension, which really was very sensitive. But we see the WC2, JP0, max PSI 50, and mortality rate parameters showing very high sensitivity. And also like they also show significant high uncertainty within the model simulations as well. And one of the interesting findings for these studies are revised parameter range, that is using the the SUFI framework, we are able to constrain these parameters into new ranges. And some of these new ranges, they are very different from the default. Like we see the red lines showing the default ranges, while the blue lines show the new revised ranges. And these are also like very sensitive parameters, and this was very, very interesting too. And the other thing that we looked at was, yes, we have these new values, but how do they compare with the observations? And the leaf CN, the leaf carbon nitrogen, which is a less sensitive parameter, but the default values and the bounds, they sit well above the observed traits, distribution traits. And this was very an important finding for us, because it doesn't matter how much we continue perturbing within this range, because it sits outside the observed range. So probably this is a parameter that we might try to explore, extend the range to see what happens with does it become even more sensitive, or does the model respond to that? And the leaf dimension, especially for PFD1, which is also a very highly sensitive parameter, we also see improvements where they improved the calibrated value changes from the default. It's also different from the default, and also moves towards the median of the observed data sets. So what we found during the multi-site optimization, one, we have a revised posterior parameter ranges, and also like this from the observations, that when we compare some of those parameters with the observed traits, we do not find we don't have the compensating effect. And also we are getting closer to solving the long-standing bias in CLM, especially in ET, and there is a lot of encouragement from the broadleaf deciduals, but for PFD1, we are trying to understand why we don't see as much improvements, but we're thinking maybe largely it's because of the differences, or the sparse distribution of these sites. Thank you so much, and we're also looking forward to testing it like at regional scale or global scale, and see what's going to happen if our optimized set for these PFDs is going to improve the regional simulations. Thank you so much.
Great. Thank you so much, Thomas. I think we should move on to our last talk, and hopefully we'll have a few minutes at the end for a discussion where we can also ask these speakers questions. So our next speaker, also remote, is Ignacio Laguirre. I think I saw that they're here. Ignacio, are you there?
Yes. Can you see it?
Are you able to share screen? Excellent. Okay, go ahead.
Yes, thank you very much. So my name is Ignacio, and I'm going to present very similar results. So I'm glad to be in this session. I'm glad to be able to present these very preliminary results about how trying to narrow parametric uncertainty using land models. So I acknowledge all the different authors in the process and try to introduce a bit the problem. So there was this paper, the same paper that was mentioned before, this number 2 that shows that the performance of models in turbulence fluxes wasn't great. The different models would outperform by similar regressions or by LSTMs. However, even in the same paper, they suggest these results can be improved through calibration. So how much and how this performance can improve is quite interesting. So comparing different calibration approaches. So the first part, I use 124 sites, which I divided 50% for calibration. The other 50% for calibration, so I exclude the sites with less than 2 years to have at least 1 year for each. So the first part is using SUMA, the second part of the representation is using CLM. So SUMA is a process-based model, conservation of mass energy, multiple options. And so the first part, we have different calibration approaches. So we have this, the simple side approach by Walsh and Tang and the Good. And then we have the large sample emulator with many sites. Then we have 2 benchmark calibration, the DDS and a genetic algorithm, plus 2 LSTM benchmark, a lower benchmark, basically with one site at the same time, like a SSE for LSTM, And then upper bound benchmark, it's basically a large sample emulate, a large sample LSTM with all the sites at the same time. So the methodology is simple. So we have a simple size, we run a model, we turn an emulator, optimize this emulator, and run the